I'll show you some of the capabilities of the center. First, I'll be doing just an overview. Then I'll come back with each use case to do another short demo that will go into some specific data. So as you can see, we have a navigation bar at the top. It has the beta tag indicating that we are in an early stage of the center, data catalog, data analysis, data insights, a hub. There's about, and I can't even see it myself there. There we go. And contact us. If you hit the contact us, it will bring you to a form to complete. This will be if you've ever had a question, you find a problem with the site, or you just have an idea or suggestion for the site, you can fill this in. It will go directly to our support desk, which we handle down at NASA Marshall. Then we have, and if you're interested what this is, by the way, there's always a little eye that you can hover over and it will expand and tell you that this was a figure by the Scientific Visualization Studio of global atmospheric carbon dioxide in January 2021. We have a small welcome message, a link over to a story about the GHG Center, and then 3 focus areas with a short description of each focus area and a specific link to data sets relevant to that focus area. You can get directly to the data catalog either from the navigation bar or through this link here. And if you'd like to learn more, we pop over to the About page. This is the About. You can also access it from the navigation bar. We'll talk about the US GHG Center. We'll identify the partners. And at the very bottom, it has, again, the link to the feedback form. And if you click here, subscribe to news and announcements list, that is the same as the QR code you were shown earlier in RG's talk. It will take you to the form in order to sign up for the various focus areas. And again, we handle all that at NASA Marshall. So that is an introduction to About. If we come back, as always, you can get back to the home page. And I wanted to point out that each of these 3 areas, if you click on that, it will go to a data insight. A data insight is a type of story with specific content and text. I will take you through one. For right now, we'll go through the tracking greenhouse gas cycles story. And we have an introductory paragraph that is written at the general level. So this would be about 9th to 12th grade level of understanding. And then go into a little bit more detail in some of the paragraphs. We have figures that are interactive. You can click on anywhere in here, get the value of CO2 over time from the NOAA Mauna Loa Observatory. We have videos that will play on a click, that will coordinate with the text next to them. We have also what's called a slider. In this case, we are showing the net ecosystem exchange from July 2011 on the left, January 2011 on the right. Quite the reverse. My apologies, that's the reverse. And then again, another movie. This showing the total CO2 flux. Some links to some of the data. A discussion about natural sources of methane. And this is what we call scrollytelling, where a map will come up, and as you continue to scroll, information appears related to that map. As you scroll further, you'll see another area of the map associated with the text. Some of these can be longer, and some of the other data insights, the scrollytelling part is longer. There are links to other sources of information and other data sets, and another interactive map. This one you don't have to click at all, it auto runs. And that would be the end of data insight story. Next, I'll take you to the data catalog. Here, this contains the 13 data sets. You can sort easily. You can use simple text, and it will highlight any data set that has the text in the name or the description, and it will filter those to just 6 that match that. You can filter also by the focus area. We also have an additional category called socioeconomic, as we have some data from the NASA CDAC in here. You have the sources, the gas. If we click, you can see the gas is filtered to just carbon dioxide data products. You can always clear your filters. There's a product type, so you can look at gridded inventory, ground measurements, model output, or satellite observations. If we chose gridded inventory, it would take us directly to the EPA US Gridded Anthropogenic Methane Emissions Inventory. As you can see, it's fairly simple to use. You can, as we anticipated a growth in data sets, there will become many, many more. That's why we have the filtering capability to make it much easier to find the additional data sets. I'd like to take you into one data set for now to show you. Actually, I'll pop back here. This is the data card. Every data card has the same content. It indicates the agency, which is the source of the data. It also has the long name of the data, the short description of the data, and the focus area that it belongs to. In addition, you'll see 3 dots. If you click on it, you'll get the option to go directly to Explore, Learn More, which is our overview pages, and go directly to Analyze Data, which you'll see later. If you click on the card, it takes you to the overview page. And as you can see, then it has a link to Explore and the same access data link that we'll demonstrate later. Again, very short description and the full name of the data set with all the tags that it has. You can see these tags here of topic, source, gas, product type. We have an introduction that again is aimed for a more general understanding. Then we have bullet points. The same bullet points exist for each of the data sets. So these are standardized pieces of information that are needed to know right away what data you're looking at. This is temporal extent, temporal resolution, spatial extent and resolution, data units, data type, data latency. On the right, however, we have a section labeled scientific details. What happened is a lot of these data sets have very detailed information. We felt we wanted to separate out the more general approach type reader who wants to understand the data set at a high level, but yet still meet the needs of the scientists who need to know some of the guts, the details. So we've separated that into 2 sections, and the scientific details takes care of some of that. We have the source data product citation. So that will be a direct link back to the source data. We have data set accuracy statement, disclaimer, the key publication for the data set, any other relevant publications, an acknowledgement, a license, and then a data stewardship section at the bottom. All of the data sets have this on their overview page. So it's all quite consistent. The data workflow is a diagram indicating how we obtain the data from the data provider and bring it into the center. We have data transformation code that will show the code used to take it from the source into and turn it into cloud optimized GeoTIFFs that are used in the system. And next we have our verification and processing report. This is a PDF report that indicates the background information about the data, the transfer confirmation, the data intake process, overview statistics to ensure that the original data and the transformed data are consistent, figures to demonstrate that from a sample of the data. Again, more statistics for a particular time period as a random check, and then some other useful links to the user notebook or the overview page. So every data set has this to ensure that users understand that we have checked and verified that the data we're presenting here matches the original source data. We feel that's very important. And for now, I think that's where I'll stop because I'll be showing you some of the other capabilities as we move along. So thank you.
Thank you very much, Deb. Now I'm going to hand the screen back over to Allison and Alex. We have some Mentimeter questions for you. So there are 2 questions that we have on Mentimeter. And again, you can access the Mentimeter with the information in front of you there. The code is on the top and the QR code for the folks in the room. Please go on there and you'll be able to see the questions and try to answer. Okay, so we wanted to get a poll of the room. We knew who we invited, but I wanted to just make sure that you guys self-categorize. What type of GHG Center user are you? And we have a few options here for you to select. So I'll give you everyone a couple of minutes to do that. And while you're in there, please take note of the Open QA button that's at the bottom of your screen when you're entering. That's how you can ask the questions of us, and you can vote on the questions that are already there. So that's how we'll start to adjudicate the questions that come in during the panel, which you will see later on today. All right, we got a good set there. Let's move to the next question. Or to the next one. Yes, so you've seen that portal that Deb was so kind to share. We have, what is your intended usage of this portal? Now you probably can't answer that just yet, but take a look and see if there is something you can share with us related to that. And we are always open to comments and any initial feedback you have. RG was kind enough to share a few of the areas where you can provide us with comments and join user focus groups. We'll put those back up throughout the day so you can do that. But there are Google Docs available or Google Forms available for you to provide us with comments. Okay. All right, so we'll move on to our first focus on gridded anthropogenic greenhouse gas emissions. We have a panel of speakers here. These topics that we've chosen for our focus areas, they were for the first phase of the center. As I mentioned, we're in our beta initial stage. And as we go on over the next few years, additional topics and data sets will be added to come. So after we have this first presentation topic, and I invite our panelists to please come to the stage, there will be a brief break. And I remind you to check the Mentimeter regularly because we'll have more polls for you throughout the day. All right, and I'll turn it over to Dr. Bowman or EPA colleagues.
Thank you for the opportunity for us to introduce the first of 3 demonstration areas with my colleagues. First, next slide, please. We're going to quickly go over this exciting new data set that the EPA has been leading on this gridded inventory. And then we're going to have a chance to show how you can interact with this inventory. And then secondly, after that, we're going to talk about the different agencies' contributions, really just a morceau of what these agencies bring to the table in this space, followed by an opportunity for you to ask questions and interact with this first problem. Next slide, please. So I think first of all, it's important for us to ask why we are here. What's the purpose of this meeting? And that can really be described in these first 2 slides, or these first 2 charts. Over our lifetime, the increases in concentration is exposing us to concentration levels that are unprecedented in our entire history as a human species. This has led to a planetary rate of imbalance, about almost 1 watt per meter squared, which has altered the trajectory of our future. And it's for this reason that the IPCC has affirmed, as it has in the past, that there is an unequivocal relationship between anthropogenic emissions and the temperatures that we are experiencing and will be experiencing in the future. Now, the ultimate test then of any mitigation policy is, can it bend that curve? And any information system, the ability to have an unbroken chain between the actions that are taken and the curves that we see here. Next slide, please. Next slide. I think I'm missing one, but go back, please. Thank you. So the bedrock of our understanding of anthropogenic emissions comes from the inventory compilation process. We've already heard about that. That's been going on for over 30 years. And that will be the basis of discussions, for example, at the COP starting this week, about how to mitigate emissions and how to have collective action internationally as well as nationally. But over the last decade, we've seen an actual sea change in our observational capacity to understand and directly measure concentrations at multiple scales. How do we link then this new technological capacity with the underlying structure that we've used to understand climate mitigation? That will be the subject of my next colleague, Dr. Erin McDuffie, where she'll introduce the EPA inventory gridded process. Thank you.
Perfect. Thanks, Kevin. I'm Dr. Erin McDuffie. I'm a physical scientist in the Climate Change Division at the US EPA, and I'll be talking about the EPA gridded methane emissions inventory that we developed and is featured as use case 1 on the GHG Information Center. So next slide, please. Okay, so the gridded methane emissions inventory is first and foremost a spatial representation of the US national greenhouse gas inventory. So I wanted to make sure that we're all on the same page and kind of set the stage with what the national inventory actually is. So we've already heard about this product a few times today, but it's a report and data set led by the US EPA. However, it has contributions and support from many other agencies, also research institutions, industry, et cetera. And what it actually is an annual report and data set that represents official US greenhouse gas emissions data in the context of reporting to the UN under the Framework Convention on Climate Change. And it represents national anthropogenic greenhouse gas emissions for 6 or 7 different greenhouse gases and over various economic sectors. And it includes a time series of emissions that span all the way from the year 1990 all the way through the current year -2. So the inventory that was published in April of this year included emissions through 2021. So it is submitted to, back the slide, please. Yeah, thank you. So it is submitted every April 15th to the UN as part of the UNFCCC framework. And it has been reported by the EPA for over 30 years now. And one point I wanted to make here is that every year we do go through an annual development process, but we're not just tacking on an additional year. Every year we're actually recalculating the entire time series of emissions, and that's so that we can incorporate methodological updates or updates in underlying data sets that we're using. And I'm not going to go into any details here and exactly how this inventory is developed, but it is developed using internationally agreed upon methods from the IPCC, Task Force on Inventories, and these are methods that typically rely on activity data and emission factors. So next slide, please. Okay, so as I mentioned before, the gridded methane emissions inventory is first and foremost a spatial representation of that national product. The reason we developed this, which I'll touch again on in my last slide, is that we wanted to develop this product to facilitate more direct comparisons between national inventory emission estimates and those derived from atmospheric observations. So what is actually included in this gridded data set? It includes annual maps of emissions from over 25 different inventory source categories. And it is consistent with the national inventory, which means that if you were to sum all of the gridded emissions across the CONUS, those would equal the CONUS level emissions that are reported in the national inventory for each of those 25 plus source categories. The way we develop this is first by taking the national estimates and then spatially disaggregating them or allocating them down to the state, county, and grid cell level using a series of proxy data sets. And those proxy data sets are meant to represent the spatial distribution of methane emissions. And where possible, we actually use the same data that is used to develop the national inventory so that this gridded product can be as closely as possible a true spatial representation of the data and emissions in the national report. And then this data, this data set is not developed solely by EPA. This has been built out of a now, I think, decade-long collaboration between US EPA, researchers at Harvard, Brom Massacres at SRON has been instrumental in this work. And this update that we're talking about today is actually version 2 of the gridded data set. Version 1 was published in 2016, and that effort was led by Brom out of Harvard at the time. And now we've finally completed an update to version 2. So next slide, please. Okay, I don't want to spend too much on the actual results or what's in this data set because you can now all explore this on your own. And we also have a paper that was published last month in ES&T that I encourage you to read. But I just want to highlight that different sources do have very different spatial patterns. This figure here is from the paper, and it's showing the emissions in 6 aggregate source categories. And so you can see, for instance, natural gas and petroleum systems, those have spatial patterns that are more reflective of where the oil and gas production basins are, whereas waste emissions, for instance, are much more centered around individual facilities. Next slide. Okay, and then to finish up, I just wanted to highlight again, reiterate why exactly we are going through the effort of developing this gridded product. As I mentioned before, it's really to help enable comparisons or more direct comparisons between EPA's national inventory emissions and observations of atmospheric methane concentrations. So next slide. This is an animation and I thought I would have control of the slide, so apologies. But in essence, it's very difficult to compare these two estimates because you have the national inventory, which reflects total national annual emissions of, in this case, we're talking about methane, compared to observations, which I just have an example of satellite data on the upper left. And those observations are made at a particular time and place. And so it's difficult. You're talking about different spatial and temporal timescales if you want to compare the two. I think next one. Yeah, so how do we do this comparison? Next slide, or next. One way to do this is through an inverse analysis, which actually requires a gridded estimate of emissions as a prior, which then can be combined with atmospheric observational-based data in order to optimize the emissions in your posterior or your final product to optimize those emissions to best match your observations. So you use this prior to kind of get at an observationally derived best estimate of what your emissions are. And then next, this is my final animation. However, at EPA and the inventory team, we're interested in closing this loop. And so you could do this inverse analysis with any sort of gridded emissions product as your prior, but we think that, it's important if you want to feed back into the national inventory process and use this observationally informed data to reduce uncertainties in your inventory or verify or improve your inventory. You need your prior estimate to actually reflect the information that was in your national inventory in the first place. Because if your prior emission estimate doesn't actually reflect the spatial patterns or source emissions that were in your national inventory, Then when you're to the point of kind of closing this loop and comparing your observation-based or observation-derived emission estimates compared back to your national inventory, you could bias your interpretation of those results if your prior doesn't actually reflect the data that was in the national inventory to begin with. So next slide. I think that's where I'll end. Now we're going to get a demo from Deborah, but thank you. Happy to answer any questions about this data set and happy data exploring. Thank you.
Thanks, Erin. Okay, wrong glasses. Sorry. Let's get out of here. Come back to our page. It's not sharing. I have to share first. Thank you. Okay. So for this, you would access the EPA data by going to the data catalog. You could choose a data product of gridded inventory, bring it right up. That's one option. Otherwise, you could simply go down all the way to the name of it. It's alphabetical. If we click on that, you will see that there's an Explore button. You click on the Explore button, and that takes you into the Explore environment. The first time you come here, you do get a disclaimer, and that is the same for data analysis and any Explore environment areas. And that is to remind everyone that the data you're looking at is within a mapping environment. And you can currently only see one data set at a time. We are working on a new capability, excuse me, that will allow multiple data sets to be envisioned at the same time. But that is in development. So that will be one of the improvements that will be coming in the near future. So you click I understand, it goes away. You probably won't see it again unless you're on another computer with another instance of the website. Here we have the United States. Is there any way for me to get rid of this little box? I'm sorry, I do need to put that out of my way. There we go. I have a box you all can't see that's right in the middle of my screen. Okay, so we can take our scroll bar, and I do this better with a mouse, hence my need for my mouse today. You can scroll in and out to increase and decrease size. Same with the pluses and the minuses, though they take a bigger jump. You can search for something like perhaps Texas and hit enter, and it will zoom you into that area. So you can do that from, if you're on a global level, you can choose a word and it should find you the right place. You have a way to remove the sidebar if you'd like. There's also, again, a way to access how to use the data set. It will give you the stack name of the data set, provide you the data transformation notebook. This is the same one I showed you last time. A sample data notebook, and we will show you a demonstration of that in the next demo. It would be data browser, which will take you to the location of the data where you can get individual files, and the Jupyter Hub access. And that will be demonstrated next in the next demo. You also have a little marker here for using this data with a GIS software. You can get an XYZ tile URL or a WMTS tile URL, and all you have to do is click here to copy it and then take it into your environment. And you have the ability to turn on and off your map so that if you want to see something below, like a label, you can. The important part here, which I am showing you last, is this Earth button here. This has different ways of showing the data. Now we've defaulted each data set to something that works best for that data set, but one can play and choose different kinds of backgrounds. You can turn on and off your labels. If they're in your viewing area, you can remove them. You can turn on and off your boundaries or both. More important, especially with the EPA data, we default to equirectangular for the entire system. You can choose something like Mercator, which will in fact make the map look much more consistent with the massacres paper. And so it's a little easier then to look at the massacres paper in here and see that in fact it is the same data. What you're looking at right now is the total methane layer. There's 27 layers to this data set. So as I scroll down, you can see how they're kind of organized. We have them organized by the sectors that Aaron mentioned. There's the agriculture and then the parts of agriculture. As you hover over each one, because the width of that left bar is only so large, it will give you the full name as you hover. In addition, you can click the eye, and the eye will give you a somewhat longer description of that layer. If we look at, for example, the agriculture, that's the total of all of the 4 below it. Same for natural gas. The total is the same, is the total of all of those below it, so all the different parts. If we look at petroleum exploration, for instance, this would be the total petroleum map. If we zoom into this area, we can now look at some of the differences here by date. We have this nice feature at the top. You see that where it says toggle date comparison. If we change the date on this top one, let's say we click on the calendar item and click 2012 and click save. Now we're looking at the 2012 data. And if we click toggle date comparison, it will automatically default to giving us the 2020. Now you see the slider that we had in the data insight story, and we can slide this back and forth in a particular area to see the differences. 2012 is on the left, 2020 on the right. If we zoom in to this area, we will see the differences over time between 2012 and 2020. Another example could be done in North Carolina, where we can see, looking at the agriculture manure management, let's say. We have a large area there. Now we are in, let me make that bigger for you. There we go. You see that we've got 2012 on the left, so 2012 on the right, which is out here in the ocean. As we move left, you can see the differences. So this is one example of how you can use this slider and the 2 dates and change to different dates. And I think that's all I have for now. If you can have a panel or whatever, thank you. That's this capabilities. You have to stop the screen, right? She did it. No.
We'll have a Q&A session where you can pepper Aaron all sorts of questions about the details of those data sets. All right, so now we're going to talk about the different agency contributions that can be had, a potential for the Greenhouse Gas Center, and particularly the capabilities that these different centers or different agencies have. First one is NASA. The key thing to consider when we're looking at this problem, next slide, please, that there is an 8 orders of magnitude difference between the scale of the problem and the scales of the solution. We have a global scale problem, which will be described in the next demonstration phase, led by Leslie Ott, down to these very point measurements at facilities that will be discussed by Andrew Thorpe and company in the 3rd demonstration area. Between those two is the regional scales. And that's the scales at which often policies are being formulated, national and subnational. In the United States, there's perhaps one region that's had gotten more interest than any other. Next slide, please. And that is the Permian Basin. 40% of all oil and gas production is done in the Permian Basin. The question is how much methane is being emitted. Research being led by Daniel Verone, Dr. Daniel Verone and Professor Daniel Jacob at Harvard University, building upon investments from NASA under Jack Kay's research portfolio, developed a portable or open source inversion capability, the inverse methane inversion tool, integrated methane inversion tool, and use that with tropomi data to estimate the methane emissions in the Permian Basin at a weekly scale over multiple years. And what they learned from this was quite striking. First, the total estimate was about 4 teragrams per year. But using additional information about oil production, we found that the methane intensity dropped by almost a factor of 2. But you also see there's substantial variability that's revealed by this weekly capacity to estimate methane emissions, related, for example, to new well development or gas price crashes. Now, what this means is that an actual relationship between them is far more subtle. It's not simply that if you have more production, you get more methane emissions. Far from it. But by having this additional information in conjunction with this weekly scale data, this allows us to now relate interventions that could occur in a region to the expected concentrations that we see within this kind of a system. We would expect the continuation of this type of capability would allow us to provide the sources of information needed to be able to relate mitigations, changes in forcings to their intended atmospheric responses. The next one, we'll go zoom out a little bit further into the nation scale, and that'll be led by Dr. John Miller.
Hi, everybody, and thanks, Kevin. I'm just going to show you, give you a very brief taste of some of what we do at NOAA, using, as both Kevin and Aaron mentioned, about using inverse modeling, where we use atmospheric data. Next slide, please. And the first example is some of you may have heard of Carbon Tracker before. We have just re-released with the intention of routine operation going into the future of Carbon Tracker methane. And this project has been led by Lori Bruweiler, who's in the audience today. And in our case, we focus on mostly surface-based measurements, and those are surface-based, still means aircraft, but also remote islands throughout the world, tall towers, mainly in North America. And when we combine that, as Aaron mentioned, with bottom-up inventories, we can produce gridded methane maps from atmospheric data. In this case, one of the key aspects of this study in particular was the use of methane stable isotope data that allows us to get to some level of attribution. And what we see on the right-hand side here are both global and then a zoomed in North American map of fossil methane emissions. And this is just an example of something, this is publicly available on the web, and something similar to this is actually already on the GHG Center website. Next slide, please. Now, this next thing is something that is more exploratory. It's not yet a routine product, although we imagine it will be within the next few years, which is to use for CO2 to get fossil CO2 emissions, the same inverse modeling approach. But in this case, we're using a very specialized tracer, which is the radioactive isotope of carbon, carbon-14, also known as radiocarbon, and using those atmospheric measurements to be able to detect fossil CO2 emissions as distinct from biospheric CO2 fluxes. And using very similar processes, we can produce maps both for the United States and globally of fossil CO2 emissions here in the case of 2015. And this is just a taste of what we can do. And this one in particular is more in development. Thank you very much.
Good morning. Could you please just move the slide? My name is Kim Mueller, and I work at NIST in the Greenhouse Gas Measurement Program with James Whetstone. And here I'm today to present GRAPES, or the Greenhouse Gas and Air Pollutants Emission System. And this is an initiative that began in 2022, so it's pretty recent, through an agreement with NIST and NOAA's Chemical Science Laboratory. I'd like to just acknowledge Brian McDonald there over there at the end of the corner. So the purpose of GRAPES was to enhance the U.S. government's capability to both map and model greenhouse gas and air pollutant emissions consistently across space and time. And why would we want to do this? Why does this make sense? Well, the underlying information that we use to quantify greenhouse gas is pretty much the same to map air pollutant data. Also, you can imagine that many of the sources are the same. You can think of power plants, you can think of heavy-duty trucks, and you can think of emissions from both the agricultural and industrial sector. So when we're in GRAPES, we use a lot of the same activities that have been mentioned previously, with just a slightly different twist. So we use an activity-based approach to come up with our bottom-up emission estimates, or our prior, as Aaron referred to them as. And then we also estimate uncertainties on the emissions. That's the little twist. And it gives us some measure of how much we think we know about emissions based on the underlying characteristics of the data. We then will be evaluating those emissions using atmospheric observations, and we'll use multi-species to be able to do some sectoral attribution. So overall, the purpose of the program, or overall goal, and what we envision is to enhance the ability of the U.S. government to hindcast, forecast, and nowcast greenhouse gas and air pollutant information. And presently, we're in discussions with the center how best to interface with the center, but certainly we will be contributing data as it becomes readily available. And I look forward to the question and answer session as I believe it's starting right now.
So we've had opportunity to ask questions in the Q&A. This is our Q&A phase. And I think we'll be getting questions through the
Mentimeter.
Mentimeter, and we'll have a chance to respond to those. And then towards the end, we'll have a chance for folks to ask questions at the mic. How much time do we have, Shauna?
We still have about 30 minutes.
Okay, so about
Sorry,
half of
15
that.
minutes, 15 minutes, pardon me, and then we have a break.
Okay.
Yes, pardon
So
me.
give me at the last 5 minutes, let's have the opportunity for people here in the room to also be able to ask questions.
Okay. Thank you. So right now we have 3 questions in the chat, and I just got one that's voted up, so we'll start with that one. How does the GHG data portal plan to leverage the data sets produced by NASA's Carbon Monitoring System program and other programs?
So first of all, let me say that we're already beginning to do that. So for example, the work that we're seeing with the work that I showed with the Permian Basin is in fact work that was supported by the Carbon Monitoring System. So that kind of work, we have not yet brought that into the Greenhouse Gas Center, but that's the kind of data sets that we're going to be looking at. So there's a very strong, I think, relationship within the NASA component between the kinds of investments that are made in the CMS, how those then get matured and then get transferred into the GHG Center. The particular details we'll be working out, but that process is definitely something that we're considering.
Thank you. We have another question here, and I will pose this one. It says, have you compared the gridded methane estimates at the state level with any state level GHG inventories? If so, how did those align or not?
Yeah, I'll take that one. I think, yeah, this is on. That's a great question. The EPA now publishes, out of the greenhouse gas emissions group, publishes not only the national inventory, but also state emission estimates as well. I believe they just published the 3rd year of state estimates. So the long-term vision for national, state, and gridded inventories is that they all align. The state level inventory did not exist at the time that we started development of the gridding. So they are, the gridded inventory and current state products out of EPA are similar, but not exactly the same as is the gridded with the national. But we are kicking off the development of version 3 very shortly, and that's one of our priorities to make sure that all 3 products are aligned.
Thank you. Any further comments from anyone? Okay. Another question we had, which may be a bit more general, is what is the mechanism to submit data to the GHG data portal?
Is that something you want us to answer, or is that something that
I will
you
leave
or
that
RG
for my
will have to
colleague
handle?
to decide.
Sorry?
Would you like to speak to it, RG? The question is, what is the mechanism to submit data to the GHG data portal?
So we're currently in the, so yes, so I mean, definitely, I think we are developing this engagement where you can reach out through the feedback mechanism that currently exists on the portal. We have the user focus groups, and we're in the process of developing processes for prioritizing and integrating additional data sets. So I would say if you're currently, you have, information or data that you'd like to contribute, do reach out and we can start the discussion. Thank you.
Thank you. Okay. Another question we have, it just moved. What is the expected latency of the various data going forward? How does that impact the usefulness of the data for decision making?
Well,
So I guess we can start with the.
maybe Aaron, you can start with that one, and then we can.
I think on the EPA side, we're going to be providing updates as those become available. I can't speak to the exact date of when we'll have an update, but I think we plan to continue contributing as that information is available. And I think I heard that from all of our speakers today, that information will be provided as it becomes available.
I could just add that we're striving in the role of providing this useful information. I think RG's already articulated the role of building a capability of providing this on an expected cadence. And so it's clearly that some information that if it's 5 years late or 5 years between the time of when you need that information, the time it's available, that undermines or it compromises the impact that can have. And so while we do not have the specific dates laid out at this stage, absolutely then some of the investments that we have are moving towards building repeatable expected data product deliveries. We'll be hearing more from that, from the EMIT team in particular, but you'll be seeing similar types of things in the years that come for this demonstration area.
Thank you.
I'll just mention that with regards to, I mentioned that carbon tracker methane will be a routine product. Currently, the schedule would be every year. In terms of how that interfaces with the GHG Center, a prototype version is essentially already on the GHG Center, but we haven't yet communicated and worked out with the GHG Center how further updates will be communicated. That's an area that we'll work on. But latency is roughly, it's similar to what Aaron mentioned with regards to for various other reasons with the national inventory reports. Often it's about 1 to 2 years backwards in time at present, although we're very much aware of the need for more rapid data and we're exploring mechanisms to accelerate that process.
Thank you. Okay, another question, and I'll take here. It says, how does the EPA provide or consider uncertainty in emissions?
For the gridded data set that we spoke about today, we do have uncertainty estimates that are part of those gridded data sets. Those are available on our data portal on Zenodo, which you can get to from a link on the GHG Center. The national inventory and state level inventories also have uncertainties associated with those products, and those are all available in the public reports as well.
Thank you. Okay, we have another question that's a little similar. It says, the oil and gas sector is developing a host of technologies to measure methane emissions. How will empirical data be incorporated?
Yeah, incorporated into what is my follow-up question. Yeah, on the EPA side, there are ongoing conversations with how to best incorporate empirical observation-based data into the national inventory products, as well as the state and gridded products. We're already incorporating some observational-based information in the oil and gas sector. For example, well blowouts. We have some observation-based estimates in our national inventory, and we continue to work towards evaluating new observations as they become available.
Thank you. Another question that came in, it says, can you give examples of practical questions that can be answered with our current capabilities?
Okay, so, well, all right. I think I'll make a first cut at that. We've already, so in the example of the Permian Basin we just provided, we just showed that the methane intensity dropped based upon that research. That's pretty important, but the resulting methane intensity is about 3 to 4%. I think Daniel Barones here can clarify that. But that's far higher than the industry standard of 0.2% methane intensity. So what have we learned? We've learned, A, that the methane intensity is going down, even while as a consequence, even though gas production has gone up, but it's still not nearly high enough compared to the kinds of standards that even the industry itself would hold itself to. To me, this is very good information about how far we've progressed and how far you have to go in order to reach those standards. To me, this is quite a practical response, and one that if you monitored over time would allow you the kind of the assessments to make if you're moving towards a decarbonized system. Where are you need to put your major investments?
Yeah, I'd just like to comment on behalf of NIST. I think our purpose here is not to pose the question, but in actuality provide the data and provide the information for others to be able to ask those questions and to use the data as it meets its needs. Certainly, a lot of those will be science questions that may be addressed within individual agencies, but again, from the NIST point of view, our role is to provide reliable data to the community.
Just to add a comment on top of that, which is from the data provider perspective, right? Providing data at the highest spatial, highest temporal, highest sectoral information possible allows more stakeholders to use the information in ways to answer those questions. So all these questions about kind of what will the data look like and the latency behind it, I think is a really important thing for us to consider as we move ahead as a center too.
I guess just as a quick follow-on to that, I agree with everything that's been said thus far. From an EPA perspective, we're providing and developing the gridded information primarily as a research tool for the research community to address the various research questions that they have. But I do want to highlight that the whole impetus of the original gridded product was because there was no spatially representative product that reflected the national inventory. And so the development of the original gridded product in 2016 actually enabled a lot of the direct observation inventory comparisons that we've seen in tens, if not hundreds of papers that have been published since 2016. And so that's a very practical question of how do the observations of methane that we're seeing compare to our emission estimates in our bottom-up inventories. And so the gridded inventory has provided us a tool to answer those types of questions. And our intent with version 2 is to provide now an updated version of that data set that lets us compare observations that were made more recently to more recent versions of the inventory to kind of check those comparisons again and continue moving forward. So that feels like a very practical use to me.
Okay, thank you. And then I'll do one more from online and before we open it up to people in the room. There are two questions in here related to modeling and forecasting, so I'll try to combine them. Are there any forecasting models to estimate future GHG emissions under climate and land use change scenarios? And then the other question is, what is the role of the modeling future emissions and mitigation options to inform planning?
I'll just make a general comment in that we are really always primarily focusing on what we can do with our observations, which is look at what's happened from now until the past and not forecasting. However, the mechanistic information that we get from the atmospheric data does inform the kind of models that are used in Earth system or climate modeling that do forecast. So there is some feedback there, but I think the kind of model that forecasts future greenhouse gas concentrations, those are a little bit outside of what we in particular do and is more in the climate modeling sphere. I'll just mention that.
I was hoping that Brian can talk about the current capabilities that exist at NOAA for doing air quality forecasting and how that might pertain to future greenhouse gas forecasting as well as outlined in GREAT.
Yeah, is this microphone on? I was thinking about that interconnection, right, with greenhouse gases and air quality. So in the US, we have an air quality forecasting system that's provided daily, done in partnership between NOAA and US EPA. And for that air quality forecast system, right, it'll be as good as the emissions that you put in there. So that's not just anthropogenic sources. There's wildfires, there's dust, there's other things that contribute. But you need that information every day, right? And so it's thinking about, you know, we have operational forecasting systems in the US, right? For weather, for air quality. And I think the question might also be, how do you get the greenhouse gas piece to those type of latencies, right? Maybe you don't need it every day, but maybe it's monthly, maybe it's quarterly, right? Or at least annually, right? As far as like what is probably needed for air quality, I mean, trying to get towards at least a monthly emissions adjustment, right, would be helpful, I think, for the air quality forecasting system, if not a daily, right? So bringing in data assimilation tools, satellite data sets into that as well, especially for fires.
And I'll just follow up. NASA definitely has a lot of capacity to do projections, both at sort of the medium-term scale, short, medium, and long-term scale, such as the work that's being done at GMAO, as well as the kind of work that's being done at GISS. The details of that I will leave Leslie, Dr. Leslie Ott will have a chance that we'll be talking in the next session, and I'll just give her an opportunity to talk about a little bit more about some of the work that has been done. The GHG Center, as of right now, has not considered projections as a formal component of the center, but I think this is very good input and one that can be considered for future activity.
Thank you, everyone. Now, are there any questions or comments in the room before we take our break? Hey, yes, please come to the mic.
Congratulations. So I'm Dave Allen from the University of Texas at Austin. Congratulations on a great advance to the spatial and temporal resolution of greenhouse gas inventories. It'll be a real asset, as people pointed out for the research community. I'd like to, though, build on something that Brian just said and ask the question about what the projected spatial and particularly temporal resolution will be going forward. The demo had annual, the original 2016 inventory had monthly estimates. What are the plans going forward? Spatial and temporal resolution.
Yeah, thanks for that question. The portal itself features the annual data, but we did develop monthly scaling factors for version 2 as well for the emission sources that have strong spatial variability. So for instance, manure management is one of those sources that has monthly emissions. So that's all available in the primary data repository that you can get to through the data portal. But it's just the annual, I think to not overly complicate things, since there's already 27 layers, we just showed the annual data in the actual GHG portal.
I'm again going to pump one to Brian. because I do think that grapes will have, even though it isn't necessarily right now an official part of the U.S. Greenhouse Gas Center, when it does become publicly available, it will likely be contributed. But I think he could talk to better than I can about this, about the spatial and the temporal aspects of the grapes product.
Well, right now, the grapes product will be at a 4 kilometer by 4 kilometer CONUS. It's on the national or US EPA National Emissions Inventory grid. That said, I mean, depending on the scales that you go to, especially at the urban scale, you want to move towards, products like from Kevin Gurney's group, right, at Hestia, finer city block scale can be useful too. So I think, as I mentioned in my comment, I mean, I think it's a question of, it's feasible with a lot of this, especially geographic information system data, to go at very high spatial, right? And so there are probably instances where we want to provide that really high spatial point type of information. But then there's a balance of what can we do, say, like operationally deliver every year, right? Or deliver every quarter or month, right? And we might have to force in some of that. But right now, I think 4 kilometer CONUS is completely doable. Even 1 kilometer CONUS is probably doable. Getting finer than that, I think you'd have to ask some of the other data providers what it would take to do that.
I think also James mentioned in his opening remarks that there are also potentially, I guess RG probably can elaborate on it as well. I think plans for public-private partnerships as well, where there will be opportunities, I believe, for other data sets to be contributed to the center. Again, you'd have to refer to RG on that. And so those are going to have various, I'm not sure, but various other spatial and temporal resolution as well, I think, too.
Yeah, just add, because Dave also asked that question, right? I think there's also a lot of information in oil and gas fields as well, right? About that high spatial information on where devices and facilities are. And so I think those questions about how you incorporate the private sector into this and getting higher spatial information is also, especially for oil and gas, important.
All right, thank you, everyone. I will invite you to take a short break. Thank you to our panel, and that was a wonderful discussion. We will do this again for focus area in 2 and 3 after the break. So let's convene at 10. Thank you.
Got it preloaded, right? Got like 2 minutes. We're trying to get everything spun up. Yeah, those are some good questions.
No, they're into it. Which is
Yeah.
first one is you have one of these and nobody says anything. Hey, bring a line.
All right, man. Making sure everything works.
radar. Okay, everyone, thank you. Thank you for your enthusiasm and the wonderful discussion you're having. Our break is up. Please return to your seats. We would like to begin again. All right, thank you, everyone. Welcome back. Thank you. I'll invite my colleagues up for panel number 2. So for our next panel, we will have our focus on the natural GHG sources and sinks. And I'll invite my colleague to come up and begin the presentations. Thank you.
Thanks, Shauna. I'm John Miller again from NOAA's Global Monitoring Laboratory, and I'm going to start us off today talking about the natural sources and sinks theme within the GHG Center, and start really by going over some of the larger scale context in a similar way that Kevin did earlier. So next slide. Oh, first, before actually, not next slide, I just wanted to introduce our panelists, myself, Anna, Kenna, Leslie, and Ben, and also acknowledge Arlen Andrews, who could not be here today, who's also part of the natural teams group. So next slide, please. Yeah, so just as a really brief outline, the first half of the outline is really going to be talking about a lot of background aspects about why natural is important, because often it can be relegated in these conversations about mitigation to the background, but I think it really provides very important context for why we're doing this. And then we'll move on to the overview of the center, not the center activities per se, but more the website activities. So next slide, please. Yeah, so next slide, please. So just as a really basic context for those who don't know, this graph the red line here shows that we would already be well past quote unquote dangerous in IPCC terminology if it weren't for the oceans and ecosystem services pulling down tremendous amounts of our emissions from the atmosphere. And in this case, the calculation would show 570 ppm in 2020. And next slide. But fortunately, because of these land and ocean sink processes for CO2, we're only at 410 as of 2020. That's already about 5 ppm higher, or 15 ppm, or roughly that, 7 ppm higher now, 3 years later, as it grows and grows and grows. And so the oceans and the terrestrial ecosystems, whether that's soils or grasslands and forests, are absorbing a lot of CO2, but this process is really unknown. And this essentially 50% climate discount that we're getting on our emissions, we don't know if this sale, so to speak, is going to be continuing far into the future or not. And so understanding these processes really helps us define our so-called carbon budget, our allowable emissions. If we don't understand the natural processes, we can't define what we can control, which are the direct anthropogenic aspects of the carbon system for both methane and CO2. So next slide, please. So methane is really similar. Here we see on the left-hand side what Kevin showed earlier, that since around 2006, methane was quite flat for around 7-8 years, and then skyrocketed globally, and that you can see some inflection points that it's even rising faster as we speak. And both at the global scale, which is the pie chart on the left, and at the national scale, which is the pie chart on the right, if you look at the wetland sector, which is the major natural sector for methane, you will see that the uncertainty in that wetland sector is large relative to what we normally focus on, which are the oil and gas and the agriculture, that uncertainty is really large, and that uncertainty really limits our ability to define our mitigation targets really well. So this is the basic context that one of the most important contexts of why focusing on understanding natural processes through both bottom-up models, inventories, and top-down approaches is very important. Next slide. And so the other thing is, as I alluded to before, climate change may undermine these carbon sinks, especially in the CO2 phase. So we see images here of, starting from left to right, of fires. Fires both directly emit CO2, but also impede the capacity of forests to absorb CO2. Droughts can have very big impacts on carbon absorption, as well as with regards to blue carbon, changes in coastland wetland dynamics can also have large impacts. Next slide, please. So one of the things that people have talked a lot about within the natural space is our so-called nature-based solutions, and these can certainly help to mitigate emissions. I won't go through all of these processes, but some things are reducing deforestation, but also things like carbon dioxide removal approaches through soil carbon and ocean carbon as examples, as well as potential for in forestry as well. But really the bottom line here is that if we monitor the atmosphere and the terrestrial biosphere using combinations of ground-based approaches, whether that's inventories or atmospheric concentration measurements, or satellite remote sensing of both column CO2 and methane and the land surface characteristics, using the kinds of approaches that we have expertise in, we can help track the effectiveness of some of these natural nature-based solutions. And I think with that, I turn it over to Anna.
Thanks, John. So I'm going to talk about some of the challenges in how we estimate natural sources and sinks, which similar to those for anthropogenic sources. Next slide. So first of all, this slide shows the bottom-up piece. So there are process-based models that estimate biospheric fluxes of CO2. And an example of a time series from a set of those models is shown on the left in that plot with all the different gray lines representing the results from different models. So marching over time on the x-axis, showing a lot of spread between the models by the different gray lines, the black being the model mean, but also a lot of interannual variability. And that compared with the red line, which is the US National GHG inventory component for biosphere land atmosphere exchange, and this is just over the US. The point here is that these are the state-of-the-art, process-based, different biosphere models, and they vary greatly. And the reason for this, it reflects, this variability reflects the difficulty of how hard it is to simulate plant and ecosystem processes, which can be very complex and at very different scales down to leaf and root level. And how do you scale that up regionally and globally? So both the processes and the scaling can be quite complex, showing a lot of variability in the estimates of the US carbon sink. Next slide. But all is not lost, as John would say. We have a lot of atmospheric data that can help inform these models. So this is same as we heard in the focus area 1, for the example of methane, how we can look at the inventory and use atmospheric data to sort of evaluate that and even update those emissions to come up with emissions that are informed with the atmosphere. We can do that with atmospheric data through, this slide kind of just shows different examples of atmospheric measurements at local scales, showing an example of a eddy flux tower in Alaska, maybe measuring the fluxes from that biosphere over there. Global, the NOAA Global Reference Network, which you already saw that map before. We have NASA provided measurements from OCO. This is here showing CO2 down to airborne measurements. On the very right, we have our own NIST urban scale measurements where we're measuring same kind of atmospheric concentrations, but at high density in urban areas. And then you have also top-down measurements, sort of satellite-based measurements of things like vegetation indices, ocean color, et cetera, and those can feed into those process-based models as well. So these all can help inform our understanding of the biosphere and biospheric fluxes. Next slide. And this was really explained really well by Erin McDuffie at EPA, but here's like the bottom-up, top-down combo slide, which is that the bottom-up methods, in this case, it could be inventory estimates, but it also could be, process-based model estimates, that kind of thing for land and ocean fluxes that are driven by different kinds of data. Top-down methods being shown sort of with the blue circle, are methods that are refining these initial estimates from the inventories or process models using independent atmospheric data. And they do a really good job at constraining the total emissions that are predicted by the process-based models. And both of these vantage points are really needed to refine these natural source and sink estimates. However, as with anthropogenic sources, reconciling them can sometimes be difficult because of differences in spatial scale and in this case, poorly quantified lateral transport processes, such as carbon that's moved by rivers into the ocean. And so there's transfer in the lateral dimension as well. And but that's it, but we're working on this, and there are a variety of models, I believe, up on the portal that maybe there will be a demo after this.
Hi, everyone. My name is Kenna Rucastle. I'm from the EPA. I work in the climate change division with Erin and Sharon, and I work on the team that prepares the agriculture, forestry, and other land use estimates for the U.S. greenhouse gas inventory that's reported to the UN, as Sharon mentioned. So the bottom-up estimates of sources in sink do include these natural sources of emissions in our inventory of anthropogenic emissions through the managed lands proxies. So this is a framework that's established by the IPCC and used in the UN Framework Convention on Climate Change in these international reports that basically acknowledges that our human management decisions on lands, whether these be fire suppression or forest resource management strategies or agricultural strategies, do have an impact on these fluxes of greenhouse gas emissions, changing the magnitude or even the direction of emissions and removals of greenhouse gases from land. Therefore, we can use activity data, which for these natural emissions are the unit of activity is a unit of managed land. Most of the lands in the US are considered managed. The unmanaged lands are predominantly in interior Alaska, as well as a small portion of Nevada. So within the inventory, we use these bottom-up estimates. We use activity data, which requires pretty high spatial resolution of land use across the entire land base in the US. And we need these data across a time series from 1990 to the present. So as Aaron and Sharon mentioned, this time series brings unique challenges because we are developing lots of new modern data sources and modeling capacities and observations, but we need to combine those new modern data sources with proxy data or modeling frameworks that go back to 1990 so we can build a consistent time series of emissions across this whole 30-year period. So together with these high resolution land use maps, we use management data synthesized from in situ measurements as well. So this is on the ground measurements that are prepared by the Forest Service through the Forest Inventory Analysis FIA program, as well as national surveys through the USDA and other remote sensing imagery. We combine all of this imagery together to build these activity data databases and then apply emission factors. So what are the emissions and removals that are occurring per unit land area using process-based models like DASEN, for example. Next slide, please. And so with these activity-based approaches to building a greenhouse gas inventory, the greenhouse gas inventory has a unique strength in its ability to attribute emissions and removal specifically to these biological fluxes, to specific sources, and to specific spatial scales. So this is a graph that shows US emissions across the entire time series that are reported to the UN. And you'll see that the land use change in forestry LULUCF sector offsets about 14% of the total US emissions annually. And this amount, though, changes across space and time. It's very variable because these are natural emissions and removals. So if you have a big fire year or if temperatures and droughts impede the absorption of carbon dioxide in these natural systems, that'll be reflected in how much of a discount, as John used, is applied to our overall national estimates. And so to constrain the uncertainty and also improve the accuracy of these estimates, we need regularly updated LULUCF activity data where we want to reduce the latency and when the data is collected and when it's available to be included in the inventory. And we want to improve the temporal and spatial resolution of that data as well. Next slide. And in this figure, I really want to emphasize that it's not just a sink that we're talking about in the natural sources section. So of course, the forestry sector and a lot of these land-based sectors absorb a massive amount of greenhouse gases and contribute to that 14% offset. But there are significant sinks, as John pointed out in that pie graph, which showed that wetlands, for example, produce a lot of methane that also contribute to our national emissions. And so getting spatially gridded estimates of not just these anthropogenic, more directly anthropogenic activities, as Aaron described, but these natural sources as well, is really important to improve the accuracy of not just our sink estimations, but the sources. And I also want to point out that the data required to do this, the meteorological data, the biophysical data required to produce these spatially gridded estimates are also the data that top-down inventory approaches need to attribute those observations and those measurement and modeled data to these spatially gridded and source-specific categories. And I believe I'm handing it back to Leslie now. Thank you.
All right, thanks. Thanks, Kenna. So I'm Leslie out at NASA, and I have the tough job of saying you've heard that this is important, you've heard it's hard, and now we have to talk about what we're going to do as part of the GHG Center. And even though this is a grand challenge, this is something we're going to be studying throughout the rest of our careers because these processes, these natural sources and sinks are changing. I want to make the point that there are concrete and tangible things we can be doing over the pilot phase of the GHG Center over the course of the next year that set us up for providing better information on natural sources and sinks. So next slide, please. All right. So what are we doing first? Let's get into this. The first thing we're focusing on is improving the delivery and the quality of some of those bottom-up data sets that are coming from process-based models. Now, you might think that it would be easy to go online, even to the GHG Center portal, and find information about natural sources and sinks for 2023. It's not there yet. Typically, these models run in a research kind of mode, which is great, but often they lag real time by at least several years. And so making routine deliveries of these kinds of products, instead of trailing by years, trailing by 2 to 3 months is one of the first goals that we're already making a lot of progress toward, and we're really excited about that. In addition to making the delivery of these data products more timely, we're working to make sure that the methods that we use are more transparent. So porting those data sets to open source code repositories, making them accessible on the cloud so that everybody can see where those data sets come from, make use of those methodologies is another goal that you're going to see throughout the center. In addition, we're working across the federal partners at taking some of those process-based models and moving them from global scales down to the kinds of resolutions that we need to address state and urban scale types of problems. In some of the models that we run in our office within NASA, we might have DC and Baltimore in the same model grid cell. So imagine all the diversity of ecosystems that are mixed up there. So being able to develop higher resolution approaches is critical for meeting some of those stakeholder needs and being able to address and resolve critical processes like coastlines, those lateral transport processes that Anna mentioned. And finally, the other thing that the GHG Center is enabling is this expanded dialogue, being able to work hands-on with people like Kenna and colleagues at the EPA to understand their needs and communicate the way that these processes are represented in various types of models, because that's incredibly complex. The idea here is not to replace anything that's being done by the Forest Service, who are providing great information, but to figure out how we can complement that information with some of the advances we're seeing across the federal investments in research and applications. So next slide, please. But that's not all. So the next thing we do once we have those process-based models is confront them with atmospheric data. And this is giving us a couple really important pieces to the puzzle, right? So first of all, we basically take the process-based models, we put those into an atmospheric model, and then we assimilate data from satellite and in situ sensors that you've heard about throughout the day today. That combination of data sets is allowing us to do a couple of things, not just track how natural sources and sinks have evolved in the past, but being able to monitor recent changes in sources and sinks, both on the natural and anthropogenic side. So that's a critical piece. And also being able to provide regular feedback on the model performance so that we can ultimately refine the way that these processes are represented in step one in those models and improve them so that the information gets better. And I'll also say that an important side benefit of that, of the assimilation, the information we get on GHG concentrations, there's a couple other things we can do with that. One is to quantify climate impacts of greenhouse gases. That's incredibly important. We can also support regional modeling approaches that you heard talked about in the first panel by Brian and by Kim a little bit, right? We need good quality information at the global scales to make sure that we can support some of those more focused local efforts. And we're also proud to be contributing these data sets to the emerging WMO initiative on Global Greenhouse Gas Watch. We're lucky to have Lars Peter with us today. So there's a lot of energy, not just on the national space, the international space as well. Next slide, please. And finally, by combining all of these data sets together, we know that we can create better budgets of both anthropogenic and natural sources and sinks. And ultimately, that's what we need to be able to feed back, inform inventory processes, and being able to contribute to things like the global stocktake and the Paris Accord. So this interagency coordination that's happening through the GHG Center is incredibly important in allowing the federal government for the first time to speak with a single voice on what is the consensus view on some of these processes and contributions, leveraging the full assets across the federal government. And doing so with a full coordination on evaluation and standards for how we evaluate and bring model-based products together so that people can have a lot of confidence in the information that we provide through the center. Okay, next slide. All right, so that's a lot. That's a lot of work. And in order to do that, it's a lot more than supercomputers. It's a lot more than code. We need people, right? We need to be developing a workforce that can support not just this focus area, but the focus areas that we see across the GHG Center. And so there is this theme of workforce development that I'd like to highlight here. One of the things we're doing as a pilot effort is a greenhouse gas center summer school that's going to be hosted by Colorado State University. This summer, the first focus is going to be on modeling and data assimilation, so creating some of the data products that you heard about earlier today, but also trying to emphasize not just developing the workforce with the skills that we need to support these kinds of efforts, but being able to bring in and hopefully cultivate a more diverse workforce that brings in people who haven't been as well represented in the past as we would like, and also leveraging lots of the open source tools that Deb has been highlighting throughout the day. So next slide. Okay, so we're about to get to the fun part again, which is where we bring Deb back up for another demo. But I'll just really briefly, you can go to the next slide, highlight some of the data sets that are there and how we've prioritized getting data into the GHG portal for the beta release. You've heard a couple times today that this is a curated section. It's not every single data set the US government has supported. It's a curated example of some of these data sets. And I will say on the natural sources and sink side, that curation has been more challenging. It's tougher because there's more pieces of information to bring together than for the other focus areas. So what you're seeing here on this first release of the data portal is data sets that highlight interagency collaboration, some of the foundational observations that we use, and also data sets that highlight all of the major flows of carbon dioxide and methane. So things like the exchange of CO2 between the land and the atmosphere, ocean atmosphere, and the wetland methane emissions, and top-down fluxes that are often making use of the expertise across agencies and multiple types of data sets from the in-situ and satellite perspective. So, and I will say that's just the start. There's lots more to add and lots to update, but with that, I think we'll turn it over to Deb for the demo. Sorry, all I have to get sharing again, I think here. Okay, so if we come back to the data catalog, first thing I'm going to highlight is the NOAA data. So the design of the system is for handling gridded data really easily. And when it comes to the NOAA data and EMIT data, both of them represent more like point sources. And so we had to figure out a way to rapidly, I want to remind you all, this development was very rapid, to rapidly figure out a solution for including NOAA data and EMIT data in the system when the larger Explore capability couldn't yet handle it. So one of the things we've done is this is the overview page for the NOAA carbon dioxide data. And you get your standard information as in others. However, as you scroll down, you will find this embedded environment. And I'm now in the environment. I can put it into my own browser tab using this on the upper right here, if you can see that. It has markers, and these markers identify different stations.
So as you hover over a marker, it gives you the station location, elevation, and name. And if I click on it, you'll see the map move up. And as I scroll down a bit on my page, here is the time series for carbon dioxide from the Mauna Loa station. I can use my mouse to select an area in time. I can do that multiple times and it zooms in for me. Another way to zoom in and out is to be on the plot itself and just use your scroll bar to go in and out. You can hover over any single dot. It will tell you the date, the time, and the CO2 concentration. So that would be how you look at the time series from the NOAA data. If you want to go to another spot, you just click another station. And again, when you get down into you have to scroll down with the small screen. I do this on my big screen at home and it looks great. A little tiny laptop, you have to do a little maneuvering. And so again, you can use your scroll bar in and out, hover over any one value to check that out. So that would be the CO2, the methane has the same environment, and this would be how you would access it. Again, if you want to open it up into a bigger window, you simply click open in a new tab. You now notice I've got another tab here, and you can see that I can go out into the larger map, but then when I click on any one station, up pops my time series. So that's the NOAA data. And it's the same for carbon dioxide as it is for methane. Next, I'm going to go back to the Explore environment to show you the air-sea CO2 flux echo Darwin model data in the Explore environment. And part of the reason I want to do this is because there's, in particular, this type of data set. This is now an ocean data. So if you are looking at it in this way, it's a little hard to grasp. So if you turn it to globe projection, now you have an environment that you can maneuver with your mouse and turn and look at the spatial features in a manner that we're more used to for such large spaces. And so that is the advantage, and you can look at the poles up and down, turn it around. So that's one preference for how I like to look at this data set. Next, I'm going to go into the data analysis, which you have not seen yet. This environment is used for generating time series of data. It is not limited to any one data set, as you'll see. You're advised to step through. So step one starts with select an area of interest. And as you scroll down, you'll get a nice little map. Things work the same here as they have before. You've got a trash can, however, for when you don't like your area. Let's say I started doing this and, oh dear, no, I don't really want that. Then you click you can trash it and then click your pencil to start again. And let's say you just want to collect stuff. Let me zoom in and I'll have better luck here. Come on, mouse. And I'll, let's say, get an area. You define, you can as complex your boundary as you'd like. You double click on any point and that will close your polygon. And then you would move down to down to the next step, which is to pick a date. By default, I'll just choose these for now. We do have a couple presets over here, last 10 years and the 2018 to 2022 time period. Then you'll see it says select data sets. Really, this is going to get changed. It really is data layers because, some of these data sets have many layers, and what you're seeing is the individual layers that you might want to plot. In the case of the air-sea CO2 flux, it only has one layer, so we're going to select that one. And then also we have the methane emissions from the LPJ WSL model. That's monthly, so we select that. I want to note here that you do get a warning at the bottom that some data sets are going to be too large to use in this environment. So we have a little notice there about those two not being available. And then when you're done, you click Generate Analysis. The nice part is it has told you how many square areas you're looking at, and you can see your selection and you see your dates. You hit Generate Analysis. Yes, this is happening in real time. And so you can see the plots loading. This is coming from the cloud optimized GeoTIFFs. What did I do? Oh dear. There we go. And we have the ability to refine our search if we didn't get what we expected. We can also use past analyses. If you click on it, you can see one that I've done earlier today. It will store them. So if you, over days, you want to do a different analysis, you can just go into past analyses and bring it back up. Notice you can see that the data sets aren't temporally in sync. So to bring that in sync, you can grab one end of this plot down here and squeeze it into the space that matches this one. And then you could even do this to move it back and forth until you get what you'd like. That way you can pull it so that the two are in alignment. There's an I button, of course, where you can get more information, and a link to the overview page if you find you want more detailed information about that data set you've selected. There is a little bar symbol, and that allows you to turn on and off different statistics, but it does only do it for the plot you're on. You do have to do it for both. Right now, that would be the way to turn it on into both of those environments. And you also can download the ping for this plot or the CSV text data. Now, if you wanted both plots, you would need to do a screen grab in this version of this analysis. But if you only wanted one of these plots, you just hit the download and you can get that ping. And again, that's just one example. If you find now, I don't like these, I want to go get different data, you can keep your area, keep your time, and go and select different data sets, different data layers, I should say. Next, I'm going to bring up my colleague, Brian Freitag. He actually leads Beta, and he's going to dig in a little bit into the hub. Here you go. Is it on the piece of paper?
Perfect, thanks. Yeah, so as Deborah mentioned, my name is Brian Freitag. I lead the Visualization, Exploration, and Data Analysis platform project out of NASA Marshall. The reason why I'm here is because that was kind of used as a backbone to stand up this dashboard, the data catalog, and then also the analysis hub. So quickly, I'm going to show you an example of the notebook environment that we used. So we'll go to the OCO2 model into comparison CO2 budget overview. If you click on this access data, you see you get a number. I think Deborah showed this a little bit earlier, but we have the Jupyter Hub that's here. You also have this sample notebook. They are the same if you click on the link. The difference here is that this is a pre-rendered notebook. So if you wanted to just look at the code itself, download the data, this essentially gives you a starting point for how to access the data, run the data on your local machine, and then you can do a quick comparison to be sure that the analysis you've done on your local machine matches, what we've at least pre-rendered in the example that we've provided. So let me quickly open up the hub. Let me see, this should hopefully spin up. All right, so now we've got our Jupyter Hub environment. As a note, I did preload this. So it's not always that fast. And I'll also mention that it's currently access controlled. So we are currently using cloud computing with data that's in the cloud in the same region to essentially help alleviate egress costs. We don't necessarily want to be paying for getting data out of the cloud and onto our local machines. So we're trying to kind of bridge that gap for users to start migrating their workflows into the cloud, which is where this is. And so quickly, I'm going to hit run all, which will execute all the cells in the notebook. While that's running, I'll at least just mention that we've got a template here that kind of follows our open science principles where we provide the attribution. So you can see our authors here, both of those are UAH contractors that we have down at NASA Marshall who wrote this notebook. And so as more people continue to contribute example notebooks for data sets that are into the platform, we'll continue to use this template to kind of bring those authors in to the system. And I think almost every data set in the dashboard has these example notebooks for you to review and to use to kind of get you jump started. So the initial thing, we're just installing a bunch of libraries. That takes a little bit of time. But here's where we're actually going to start accessing the data in the cloud. So we're using our APIs to go and access the data. This stack API is just getting our the data catalog itself, hitting the data values. The raster API is what we're going to use to visualize it. We're pulling on the OCO2 MIP collection. As Deborah mentioned, there are a lot of layers that are within that. So you'll see that we filter this out for the fossil fuel layer. And then we basically are just going through here and doing some quick visualizations. So here we've got a map explorer. You can see this is very similar to what we showed in the data exploration page. You can zoom in and out as you did there. If you look very closely, we're looking at 2020 and 2019. There's a very subtle difference here just west of LA that you'll notice. You can also do the same zonal statistics that Deborah showed. This is essentially just trying to give people a springboard into the data set, not necessarily something that is going to be used for detailed scientific analysis, but it's a springboard to get there. And so now we're kind of replicating that exact same workflow, doing the same statistical analysis, and then you can see again that we've got our time series analysis showing the emission values for Dallas, Texas. So we did a subsetted area. We're doing our statistical analysis, and then we're plotting that within the browser. And then the last thing is you can, again, zoom into that specific location and then visualize it as we did before. And so all this, again, is just meant to kind of provide a springboard. This isn't necessarily something that is going to be scientific quality or science research quality and analysis that are going to be in these example notebooks. It's more meant to kind of facilitate the research for users who may be new to accessing data from a cloud-based catalog. And I think that's pretty much all that I have. So I guess I'll turn it back over to panel, I think, or Shauna.
Thank you, everyone. That was a wonderful presentation of capabilities. Now I invite you to continue with questions in the chat. Can we share? Yeah, the Q&A. So we have one question for you on Mentimeter. And what's the biggest gaps or limitations in the current information on natural sources and sinks from your perspective?
I could take a stab at this based on, and again, I'm from the EPA and work on our bottom-up inventory of land use emissions, are the emissions that are most relevant to this natural sources and sinks category. I think data we lack is especially related to these spatially gridded estimates of sources of emissions in this area. So especially with the coastal wetlands, we need to know, we lack really information even where those are, down to a fine spatial scale. These wetlands can be really small in area up to pretty large extents, and we need better maps of where they occur. We also need better observations of emissions that are occurring, and acknowledging the spatial and temporal variability in those emissions. So we need emission observations across space and time. And those will allow us to build models that we can, then just predict essentially and be able to estimate without those direct observations how, where the methane's coming from these wetlands based on maybe meteorological information or biophysical information. So those are kind of the building blocks that we use throughout the land use emissions category. And we need, I think this is probably beating the dead horse, but we need just higher spatiotemporal resolution. And we need those data to be collected regularly and and decrease the latency as much as possible so that we can be using things like the greenhouse gas inventory in real time to be tracking the efficacy and the impact of all of these natural solutions that we're implementing in domestic policy.
Thank you. And it seems like people agree with you from the responses in the room and online.
I was just going to add, so Ben Poulter, NASA Goddard, completely agree with Kenna's comments on that. I think also we need, as has been mentioned, this is a multi-scale approach to estimating greenhouse gas emissions and removals, and so we need to also have the ground data, the ground flux data coming from flux networks to be able to parameterize the models and then do the scaling with the satellite data as part of the process. For wetlands in particular, methane is wetland methane emissions are the largest uncertainty in the global methane budget, and there's concerns that there are climate carbon feedbacks, triggering increased wetland methane emissions, particularly from the tropics. And so a lot of focus on reducing those uncertainties is needed. On the CO2 side for the natural fluxes, land cover change continues to be the biggest source of uncertainty in the global carbon budget for land, and sort of improved representation of the land cover dynamics in the land surface models is needed, as well as attention to how we compare what different modeling approaches estimate for land use change emissions that Kenna mentioned with the use of this managed land proxy, which is different to how other modeling teams and assessments assess those land use change fluxes.
Okay.
One last on, and maybe a nod to Anna's work at NIST. I think one of the big challenges that we see, we of course need higher spatial resolution data and better maps. But the other challenge is when you see action, and a lot of the great action that's taking place at the state and urban levels, really being able to disentangle the natural influences and the changes in fossil fuel emissions, for better or worse, is incredibly challenging right now. We see a lot of great examples from LA. I don't want to throw any aspersions, but there's a lot of things that only work in LA because of the unique environment, unique geography. When you look at the work that NIST is doing in the DC Baltimore urban testbed, that's an incredibly challenging area. Smaller cities, less emissions, a lot more active biosphere. And I think really being able to get down to that fine spatiotemporal resolution, particularly in some of these areas that we know are changing for a variety of reasons, whether they're natural, climate driven, or because of actions. That's, to me, one of the big gaps and the motivations for a lot of the work we're doing.
Well, since you mentioned it, I'll just mention one more thing about urban areas and the urban biospheres. One of the active areas of research is to understand how the urban biosphere behaves differently than traditional, the rural biosphere or whatever, the undisturbed. So that's kind of a really active area of research, and we don't know how that affects things globally, but certainly on the urban scale, those differences can be pretty big about how trees, take up CO2 in urban areas near highways versus in a pristine forest, that kind of thing. So some of the models don't account at all, for that kind of effect. And that's something that if you're looking at the urban scale, you do need to understand. So that's kind of a very research focused answer there. Yeah.
Thank you. Okay.
One more, just to move from urban all the way to continent to global. One of the key challenges for people doing large scale, regional to continental, global scale inverse modeling is to. Okay. Yeah, sorry. One of the key challenges for people using inversely derived fluxes to convert to stock changes that are relevant, for example, within the UNFCCC framework. National inventory reports, I can talk loudly, is lateral transfer. We heard about lateral transfers in waterways, but also crop and wood trade. Those are incredibly important components that we don't have great information on now. So that actually is an emerging need for us to really make atmospheric data more directly policy relevant.
Okay, thank you everyone for those comments. Now we have questions from the Mentimeter. So again, I urge you to put your questions in the chat. And we have one question here that was highly voted. So for natural sources and sinks data, does the center envision eventually being able to support validating carbon credits at the project scale, or will this require private sector collaboration?
That is a very good question. I think there's a lot of interest, but there's a lot of dialogue needed across the federal government of the role of the center and the engagement with the private sector. So I would expect that engagement to those discussions to be happening very actively over the course of the next year. But I think right now that's still very much in the scoping phase, and that there's a lot of focus on making progress on the specific focus areas that you see demonstrated here. So I think stay tuned for more later, but I think that's kind of where we are in the process. But great question.
Okay, thank you. Are there plans to include fire emissions in greenhouse gases in the natural sources focus area?
From the perspective of the center, I'm sure that some of the available sources, implicitly reflect these emissions because, the atmosphere kind of is this seeing the net emissions, right? So if you see fluxes of CO2 and trace gases from fires, those will be reflected in those data sets. But they're also explicitly broken out in the greenhouse gas inventory, which, because it is a bottom-up inventory approach, allows for that allocation and the attribution. So we do estimate those, especially the trace gas emissions, CH4, methane, nitrous oxide, carbon monoxide, based on burned area and some modeling about the available fuels and the severity of the fire, and we can therefore estimate what that particular source of emissions within the land use sector of emissions.
Great, and I'll chime in. There's already some fire information there, and a couple of the products there are fire emissions, I think, from both the top down and one of the bottom up models. And the goal is also to be updating that information. Fires is actually one of the types of emissions data sets where we do actually have good, timely information already. Not to say that it's perfect, but we need that for understanding air quality and for being able to support a lot of the wildfire research that is also going on throughout the federal government. So you can see a little bit there now and expect to see more of that in coming months.
Okay, thank you for those comments. Let's see, here's another one. Thinking about bottom-up estimates of natural sources and sinks, different approaches can produce very different maps. How can we provide a range of information without confusing our portal users?
Do you want to take that, Ben, or do you want me to?
Well, I can take a start. I mean, yeah, that's a great question, and I think in the last 2 or 3 years that there's been a lot of research activity that's been focused at reconciling the top down, the bottom up, and the inventory approaches. I could imagine that the Greenhouse Gas Center could provide some educational tools on how to align the 3 approaches and to explain why the differences are there, and potentially sort of include in the Jupyter notebooks a way to do that aligning by the users. And like John has mentioned, the lateral fluxes for the aquatic and trade play a major part in that reconciliation. The way that we're defining the managed land proxy, the different sectors, it's sort of a complex crosswalking, but there's been a lot of advance to be able to do that.
Yeah, just to follow on, I agree very much with what you said, Ben, and I think this question is really excellent because I think it raises a much broader question for the GHG Center and many of us who communicate science on a regular basis, which is communication of uncertainty more generally. And I think this is something that we often shy away from very much. I think because there's no good answer about how exactly to communicate uncertainty in these topics, because we still are dealing with a lot of uncertainty that reflects the fact that these different, even after you try to make it more apples to apples, there are still differences often. So I would just pose that as a question for us to consider who are involved with the GHG Center about how exactly to engage properly with the public and the policy community in terms of communicating uncertainty.
Yeah, and I think it's a really good question, and I don't think there's a single right answer. There is this tension between open science showing transparency of methods, showing all of the data sets, versus providing consensus information that some stakeholders need. And you sort of have to try to do both of those things, which is challenging. So what we're trying to do through the GHG Center is to keep the GHG Center data portal as the place to provide the most curated, ideally the most consensus information when we get there, but also to leverage some of the other data systems advances that we see within NASA, within NOAA, across the federal government, to be able to provide an on-ramp for those new and emerging research approaches that also give us a little more freedom to show how different data sets are working, even if they are not at that highest tier of maturity that makes it into the GHG Center portal, right? And so that's a complicated way of saying you want people to have access to all of the information, but not to be confused by it. So I think in combination with the storytelling, the data insight that Deb showed us really beautifully today, I think there's a way to get there. The other thing that I think is really important that we're emphasizing through the GHG Center effort and through some of the things like the WMO G3W is to make sure that we have very good benchmarking of the modeling products that we're demonstrating so that people understand strengths and weaknesses and how to use them, right? And so, for example, Ben's group have been doing this amazing job of sort of operationalizing their land surface modeling, which is giving us CO2 fluxes and methane emissions in a more timely way than we've ever had before. So this is super exciting. But the other thing that's really great is they're bringing that with an uncertainty estimate from a variety of approaches within the same modeling framework and running that through an established benchmarking package that's been developed through the Department of Energy so that we can make those kinds of benchmarks and statistics available, not just for Ben's LPJ model, but for other models so that everybody can see and understand when we do have different types of modeling products, what are they doing well? And that's the first step to getting to a consensus estimate is just really having that level playing field of understanding the performance.
Thank you. Now we're at time, but I'm going to ask this one question because it's highly voted and maybe others can step in to answer it as well before we switch panels. Is there a plan to fill emissions data gaps, for example, wetlands data, with federal funding for sustained mapping and monitoring? Some states have intermittent monitoring programs, but funding is lacking. I guess I'll leave it for anyone who want to pick that up.
I don't know that I have the capacity to answer that or that any of us are able to answer that question. I don't know, RG, if you'd like to say anything, but I'm not sure that that's maybe above my pay grade.
I don't know if it's within my pay grade. But yeah, so I don't believe that we currently have such plans, and I would have to probably defer to others within our agencies with respect to that. But in our current plans, we do not have such plans yet. Thank you.
Thank you, everyone. Thank you for your questions. This was a wonderful discussion with everyone. Thank you for your time, everyone. And I would like to transition to our third panel. Now, our third topic is looking at the new observations for tracking large emission events. And I'd like to bring our panelists up and get their presentations going. Thank you.
I'll stay up here since I'm going first. All right. Thank you so much. Welcome to the discussion of our last focus area. I'm Dana Chadwick. I am a scientist at NASA JPL, and I'm just here to kind of set the stage for us to think about this focus area on tracking large emission events. So just to kind of give an overview, we're going to kind of give some background, and we're going to highlight the use case associated with this, which is the EPA's greenhouse gas inventory, and how we might be starting to integrate some of these measurements into that, and then talk a lot about the data that are available so far on the greenhouse gas portal and where we're hoping to go from here. So, all right. Thanks. So in recent years, large emission events have been increasingly identified by both satellite, airborne, and ground-based measurements. And so this focus area is really associated with focus area 1 as far as kind of anthropogenic-based emissions, but is really kind of concentrated on these large emission events that can occur for a variety of different reasons. And this focus area currently includes one case study, which is focused around the US greenhouse gas inventory, but is kind of continuing to consider other potential case studies in the future. So. And just to foreshadow what I think Deb is going to show you, this is the kind of landing page for currently the data story associated with covering large methane emission events. And so these data right now are being, the data that are being highlighted right now are from the EMIT mission. And so that's what you're seeing here, if you want to go ahead. And there's been a lot of interest in these data of late, and there's kind of a large and increasing number of users that have been focused on thinking about both airborne and spaceborne data sets. So thinking about national inventories, there's been international efforts
local monitoring and then operator self-monitoring. And these aren't necessarily things that are being done currently with the Greenhouse Gas Center, but these are groups that have been using these types of data for a variety of different purposes over the years that we're interested in kind of continuing to support through Greenhouse Gas Center activities. And so there's kind of two things that we can often think about using these types of data for. And one of them is to answer the question, is there a large methane enhancement event at this particular location at the time of observation? And then there's another one, which is thinking more about how much methane has actually been emitted, either kind of at a moment in time or over the course of a leak event. And so there's different kind of information that we need to answer these two types of questions. You want to go ahead? And so these can help people answer different types of things. So, and different types of actions can be taken. So the first question here can allow for mitigation in some cases. So operators can send technicians out into the field after an observation has been made to respond to those. There's a lot of potential where agencies can be using these data to do ground-based assessments. And then for the kind of other example, we're thinking more about how much methane has been emitted from a location. That's more along the line of inventories that Melissa is going to speak to in a moment. So go ahead. And so I just wanted to kind of set the stage for where we are currently with the Greenhouse Gas Center. So we are here where we are, ingesting emit data and being able to highlight locations where there are large methane enhancements at given points in time when emit is observing. But we're working towards getting to understanding kind of longer term emissions associated with these large emission events. And that's what's been really great about being able to collaborate with my colleagues here, and that we're continuing to work on trying to best understand how to incorporate these data in a way that gets us to these kind of understandings that'll be more useful for folks like the EPA. So I'm going to now turn it over to Dr. Melissa Weiss, who's going to speak about the U.S. Greenhouse Gas Inventory.
Great, thank you. So I'm Melissa Weitz with EPA's Climate Change Division, and I'll talk a bit about how we are currently incorporating large emission events into the inventory and future plans to incorporate more. Next slide, please. So the inventory, as Aaron and Kenna walked through, represents national total anthropogenic emissions and sinks. There are anomalous large events that can occur across different methane sources and can have highly variable emissions that wouldn't necessarily be captured with our standard approaches to develop the national level greenhouse gas inventory. So to incorporate this information, we separately, using other emissions data sources and additional information, incorporate estimates for distinct emission events. So we first did this in 2017 using information developed by CARB, compiled by a number of studies for the Aliso Canyon, California well blowout event. In 2022, we worked with a number of researchers that used primarily satellite and other information to develop estimates for 3 large well blowout events in the production segment of natural gas systems. And so we used that information to incorporate those distinct estimates into the inventory as well. Next slide. So there are a number of challenges to incorporating this information. So we know that there are many large events out there. A lot have been identified, but only few have been quantified in research efforts and incorporated into the inventory. So what we are looking for is a sustained effort to quantify large events. And noting that the inventory is a time series that starts from 1990, and we try to update the inventory every year with improved information. And so we are interested in information all the way back to 1990 and moving forward as well. So the US GHG Center is going to help us with this challenge in 3 areas. So first is identifying and assessing available satellite and other information on large emissions events. Second is developing an approach to quantify methane emissions from available information. And then third, systematically calculating the event-specific emissions estimates that we can incorporate them into the greenhouse gas inventory. I think that concludes the overview of that use case within this focus area. I will turn it back to Dana, or to Andrew.
Great, so my name is Andrew Thorpe at the Jet Propulsion Laboratory. And really happy to be discussing with you today current methods and data sets that will be part of the Greenhouse Gas Center. Next slide, please. So remote measurements of methane have been in the news over the last few years, last year or so. It's not been years yet. So we've got examples from a Reuters piece that's focusing on a landfill in Iran. And on the right, we've got methane from Turkmenistan oil and gas emissions. So it's great to see the visibility, but we want to talk a little bit about how do these types of technologies work. The next slide, please. So there are many different ways to measure methane point sources. So maybe we'll start just with what is a point source. So a point source for methane is typically emitted from a discrete location on the ground, maybe a meter or a few meters in extent, generates a concentrated gas plume that can be quantified using different technologies, right? We've got in situ measurement strategies, sampling the air. They can be deployed on ground-based driving surveys. Can we go? Yep. Tower-based systems, as well as instrumented on drones and aircraft. There's also remote sensing measurements. These can also be used on the ground, camera systems, but there's also airborne and spaceborne technologies here. So the focus for this point source emission portion of the U.S. Greenhouse Gas Center is really focused on the remote sensing technologies from satellites and aircraft. Next slide. So how do we measure these point sources? So for in situ measurements, we can take direct sampling of the atmosphere, either ground-based or aircraft-based. So there's concentrations in an XYZ space. We can use that to estimate emission rates with some assumptions regarding mixing layer heights and wind speeds. The figure on the left shows one example of that type of methodology, doing a corkscrew at different altitudes to quantify methane emissions from a landfill, as an example. There's also remote sensing technologies that measure light and the interactions with greenhouse gases. There are active systems that use light, like a laser as a light source, and passive systems that use the sun, as an example. These technologies output these two-dimensional maps of plumes. What I'm showing on the right-hand figure there is a set of methane plumes from Turkmenistan observed from EMIT. And we can ultimately estimate emission rates from this type of imagery if we incorporate wind speeds. Next slide, please. So I did want to talk a little bit about the EMIT instrument. This is on board the International Space Station since July of last year. This has a wide field of view, 80 kilometers across, with a 60-meter spatial resolution to allow us to map out methane and CO2 point sources. How do we do this? Well, there's distinct absorption features that are present in the shortwave infrared. It's a little small, apologies here, but in the center panels and the upper panel, you can see methane absorption features between 2200 and 2400 nanometers, as well as CO2 below that at shorter wavelengths. And these are diagnostic spectral fingerprints that allow us to do quantitative retrievals on a per pixel basis to map out these methane plumes and to ultimately estimate the emissions. Next slide. So we've been working in this space for about 10 years or so. In graduate school, I was able to publish one of the first papers demonstrating AVERIS, the airborne instrument's capability for mapping methane offshore in Santa Barbara and onshore in the Inglewood oil field. I did want to make a special thanks to Jack Kay at NASA for his support of these early airborne campaigns. Since then, we've demonstrated the capability using Hyperion, satellite instrument for the Aliso Canyon blowout. More recently, we've had really exciting sets of work that have come out of the California Methane Survey, and that's Riley Duran from Carbon Mapper led that project to quantify emissions across different emission sectors. More recently, we've had a paper that just published in the last 2 weeks for EMIT for methane and CO2 observations and the ability to pinpoint by sector across 2 gas species, methane and CO2. And then finally, we're starting to use AVERIS-3, which is an airborne instrument for methane and CO2 mapping in the Western United States. So given this track record, we've been able to leverage all of these algorithms and methodologies to sort of hit the ground running with the Greenhouse Gas Center. Next slide. So let me talk a little bit about our current and future data products. So apologies, there's a lot of information here. Hopefully you can read it. I guess you can. If we focus on the flow chart on the left, that's our data processing from raw radiance down to calibrated orthocorrected radiances through to methane enhancement maps and delineated methane plumes. We are making all of this data available. These are available through the land processing DAC. So if anyone wants to replicate our results, they can do so. We also have open science repositories for all of the code that is used in our data processing. The methane plume imagery that we're showing here, these two examples, are being made available through the LPDAC and will be incorporated in the US Greenhouse Gas Center when it launches. Currently, we're focusing on methane plumes, making them available, but going forward, there'll be more offerings. We will be including CO2 plumes, emission rates for methane and CO2 with uncertainties, additional data products that we will define by working with our partner agencies, like folks like Melissa from EPA and others, figure out exactly what they need and if we can accommodate them. And then ultimately, AVERS 3 airborne results are something that we'll be delivering as well. Next slide, please. So EMIT coverage currently is international, but it's spatially incomplete. So we focus on the image in the upper right. The white areas are associated with the prime mission of EMIT, and that was to define or to map out the surface spectroscopy of the arid regions of the world. Luckily, we have co-located expected regions for methane and CO2 point sources, and that's why we've been able to generate so many interesting data products to date. The ISS does have a repeat revisit, which is very important, and that's shown in the lower right-hand figure. That can be on the order of a few overpasses to many overpasses over a one-year mission. And that's important for characterizing emission variability over time. And I did want to emphasize that EMIT will have an extended mission starting in December, where we are in the process of actively redefining the areas of focus. We'll be focusing on areas between plus and minus 56 degrees latitude, and that's demonstrated by those dotted lines in that upper right-hand figure, to focus on areas that we haven't mapped yet for methane and CO2. And there'll be a focus on CONUS observations as well. Next slide. So it's a really exciting time to be doing this type of work. There's a whole suite of satellite instruments and airborne instruments that have capabilities. This is a nice figure from Daniel Jacobs' 2022 paper showing the point source imagers like EMIT and the planned carbon mapper instruments, as well as area flux mappers, some of which can actually do point sources like TRPOMI has demonstrated over the years. There's also a number of airborne assets that can be used to quantify methane emissions, AVERS and the AVERS next generation AVERS 3 instrument. There are active systems like Bridger and HALO, and then there's a whole suite of airborne operations, GHGSat, Carbon Mapper, EDFs, Methane Air, and Kairos as an example. So with that, I'm going to hand it off to Steve Brown from NOAA to talk a little bit about validation activities and mission quantification.
Okay, thanks, Andrew. So as Andrew said, I'm Steve Brown. I'm here from the NOAA Chemical Sciences Laboratory in Colorado. And I'm going to talk about the role of these in situ measurements and how they relate to some of the other things we've seen in this workshop so far today. So the real advantage to in situ measurements, and in particular airborne in situ measurements, is that they provide this very nice quantitative method for measuring emissions. The disadvantage to doing things this way is that we just simply don't have enough of these kinds of measurements. So these are very useful tools for undertaking these kind of validation efforts to be sure that we understand what we're looking at from the remote sensing side of things, or that we can understand the accuracy of the emissions inventories themselves. But they are limited snapshots in time and space. And so to do this kind of work, you really need three pieces of information. The first is just an ability to measure at a particular point in time and space the pollutant concentration of interest. In this case, we're talking about methane. You need also a very good sense for the transport. That is to say, you basically need to know which way the wind blows. So you need sophisticated instruments that will tell you something about horizontal and vertical wind fields. And then the last thing you need is as much information as you can get about all of the pollutants that are related to the pollutant of interest. Again, in this case, we're talking about methane. So you'd like to know all the things that are co-emitted or not co-emitted with methane that also make up the atmospheric composition. If you have all of that, you can put that information together in a variety of ways. It's kind of shown on the left side of this slide. A traditional way to do this is with mass balance, where an aircraft might make an upwind and a downwind measurement of a particular pollutant. Understanding that wind field very well between those 2 points then is easily converted into an emission rate. You can also look, as I said, about the covariance between a particular pollutant and other things that may or may not be co-emitted with it. And this is a really powerful way to do 2 things. First of all, if you understand an emission inventory for one thing, you can relate it to the emission inventory for methane. But this also really enables source attribution. So you might want to be able to make an emissions measurement within a particular area and understand if most of that is coming from agriculture or oil and gas or urban emissions or the like. And so that's a method that really lets you get after that. And then lastly, if you know something about vertical wind fields, you can do eddy covariance. That's a technique that lets you do a very similar kind of an analysis to mass balance, but in the vertical dimension, looking at the rate at which things are advected upwards or downwards. Examples of past work that illustrates how this has been implemented is over on the right. So just illustrating the NOAA P3 making measurements in California that are instrumental in understanding the emissions from the urban sector as well as from the agricultural sector. And then also a series of measurements that took place across the majority of oil and gas producing regions in the United States to understand that emission sector. And again, that has allowed these kinds of evaluations of the accuracy of emissions inventories. So next slide, please. So that's a little bit about how this has worked. What's going on now is illustrated here. This is an effort that took place in the summer of 2023. This is AGES, which is an acronym of acronyms, or actually AGES Plus, which is an acronym of acronyms, illustrating actually really how a lot of different agencies can work together to solve this problem, right? So this is it illustrates not just the interagency efforts and the integration of those interagency efforts, but also the vertical integration you see in this graphic that takes advantage of all the different data sets and all the different methodologies to tackle a problem, for example, like methane or other greenhouse gas emissions. So the A in AGES stands for aroma. I won't define that particular acronym for you, but I will say that's the NOAA effort. That was actually a campaign on the NASA DC-8 that's all the way on the left side of the graphic there. And that was supported by the satellite side of NOAA through NESDIS. And we have the very, very detailed measurements of atmospheric composition, including all of the major greenhouse gases from the DC-8. NASA brought to the table the S in AGES, which was stacks. And in that case, they had a couple of high-flying aircraft, and those had remote sensing instruments that could then, in a coordinated way with the DC-8, provide these maps that would then work together with these in situ measurements to understand emissions and atmospheric composition. There was another NOAA effort that's not even represented in the acronym of acronyms. It's part of the plus there. That's NOAA Cupids. That's the Twin Otter. You can see all the way on the right there. I'll show you a more clear example of that on the next slide. But that really illustrates this transport piece. So that's where we have very detailed measurements of wind fields that let us do a very good job of getting at these kinds of mass balance questions. And we do that in coordination with other aircraft. And I'll point out that we did that with the UMD Cessna, which was an effort that came from the NOAA Air Resources Lab. And then, while we're doing all this, of course, these airplanes are sampling the space in between the remote sensing instruments that are above and the ground-based instruments that are below. So we're doing this largely motivated by the need to understand what the satellites are seeing, but also to coordinate with efforts such as the NIST urban greenhouse gas test bed. So next slide. And so this is just one example just to make this more concrete and show you what this actually looks like in practice. So this is New York City on July 26th of this last summer. So the top plot there, or the top graphic, shows you that NASA STACKS effort. That's the G3, making a raster pattern over New York City, and that has this HALO instrument. That's a LiDAR instrument that can measure the column and boundary layer methane. So you see where all the hotspots are as that G3 flies over New York City. The DC-8 in the lower left there is flying in the boundary layer. You can't see all the data because there are a bunch of different aircraft tracks that are actually stacked on top of each other. But that's making that lower atmospheric methane distribution measurement. The Twin Otter sees the methane somewhat differently. You can see differences in those two maps, and that's because those two aircraft are flying at different altitudes. And one of the things that Twin Otter is doing is giving us that transport piece to really try to understand those emissions. And then the last thing is this greenhouse gas urban testbed system from NIST. A very powerful new technology being developed there with these dual comb spectrometers from my colleague Kevin Cassell, who also works with me in Boulder to produce these ground-based measurements. So that's what I have. I will turn it back over to Dana, I think, to finish us up. Thanks.
All right, just one last thing to add here on the kind of intercomparison and CalVal efforts, so that just to highlight that Avarice 3, with support from the Greenhouse Gas Center, is doing underflights of EMIT currently to kind of understand the capabilities of EMIT, and then we're also doing controlled gas release experiments with some folks at UC Riverside to learn more about the minimum detection limit of Avarice 3, as it is a new instrument. And so we'll be continuing to kind of develop that understanding, as well as be contributing those data sets to the U.S. Greenhouse Gas Center, which we're looking forward to. So with that, I think we basically just wanted to highlight that there's more to do to answer these types of questions, but there's a lot of mitigation that can be done today with the information that we do have, and we're really looking forward to engaging with all of you. So thank you so much. And Deborah's going to come up and give us an overview of what you can see there today.
Thank you, Dana. Okay. Share again. Okay. So if we pop into the EMIT data, again, notice how I can use this drop down. I could have gone back to the data catalog, but I can also use the dataset drop down and find EMIT. We're on the landing page. And again, you notice, like with NOAA, there's no explore button here, right? And that's because, again, these plumes are more like point type sources. They're not gridded. They're gridded within the plume, but not overall. So it doesn't work as well in the explore environment. So what, again, we've done is a similar Mapbox embedded environment. Again, I can open it into the new browser tab. But in this case, I'm just going to work here and show how this looks. We have different plumes. It defaults to the US, but using my browser, I can, or the plus minus button, I can show the globe here. You can see that there's over 800 plumes to date from this data set. And the coverage is limited, as mentioned, to arid regions somewhat. So you see all these arid areas where there's most of the plumes. There are occasional other plumes that you can see, but most of them are in the arid regions. Next, I'm going to pop into the, now there's a nice little button here, which I haven't pointed out yet. This little circle with arrows, that's to reset, and it'll reset to the default. So if you're out in the globe and you want to come back to where we were, it would reset to the US. So that's kind of handy. And what we're going to do here is pop into the Permian Basin area where you see this big blob of and I get my mouse here to work right. Maybe I will pop out of the browser. Not my computer, I have to say that. It's always different in Alive. Come on. There we go. So we have here a big cluster of plumes. And as I zoom in further and further, you start to see that some little red hints of red outlines showing up. Again, like with the NOAA data, I can hover and I can see latitude, longitude, time observed, and the methane enhancement value. The other thing I can do is just click on it. And what the system will do is open this window. It will zoom real close in. You can back that out a little bit with the plus minus, or you simply your browser, your mouse. They have here, you'll see a time series type plot up here. I'll make use of that in another example. There's a nice inset box, which you see has an X. It can be removed or it can be actually moved aside out of the way of anything you're visualizing. It has a max plume concentration, the concentration uncertainty, a direct link to the TIFF that you're viewing, so you can actually get that piece of data. Latitude, longitude, the orbit of the International Space Station, the plume ID, and the time of observation with the date. The plot on the right, the legend on the right shows your methane enhancement that matches the grid. If I use my eye over here, I see I can turn it off. What's this good for? It's great for looking what's underneath. And you can see here that it is a well pad source of this methane emission. And you can see the full area by just scrolling out to get the size of this. Notice it has kind of two areas here. If you, again, turn the eye off to turn it off, there's more well pads up here, and some of those could be even coming from that. So there's a lot of things you can do to kind of zoom in and look at the what's underneath and what could be causing that methane emission. Now, if we go to another region of the globe, we're going to take a look over here in the Middle East. And I'm going to close that, make it go a little faster. There we go. If you come into the area of the Middle East, there's some interesting things here. I want to use an example to show you the reason we have that date time slider in there. If I click in here, notice suddenly I've got a whole lot. I'm going to close this out for a moment. I've got a whole lot of polygons, right? And so you're curious as to which polygon am I looking at? You can always know the one that the box came up that matched, that I closed that box out. That is from this polygon here because the enhancement is being visualized. There's quite a few here, so what can I do to understand what's going on? Well, I'm looking in the August 2022 timeframe to October 2023, so it's a long period of time. If I start moving this scroll bar, you'll start to see some of these polygons disappear. Okay, so this gives us the opportunity to identify what occurred when in that time frame. And if I wanted to isolate this particularly very large plume, I can then narrow down, select it. Again, it zooms in, but it gives me the detailed information I want to see. I can move this box completely out of the way. I can turn on and off the layer, and I can see that this landfill is the one producing the large plume that you see here. And the extent of that plume is quite significant. So these are just some examples. I can also do the same in, like, let's say I want to pop back to the United States and go check out where we are right now in Virginia area. And I'm not seeing my plume. Come on.
Time slider.
Thank you. Time slider. Thank you, Andrew. And there we go. We have a plume up here. and it will zoom into that plume. Again, you can move your box out of the way, turn on and off your plume so you can see what that is. And I forgot, some compressor station, is that it? I think that's what you told me. So I don't recognize compressor stations from satellite, but good to know. So that's one way in which you can look at the EMIT data here. There's over 800 plumes to choose from. Have fun. There's a lot to choose from, to play with. And I think that concludes. Now, one thing I did want to mention is that this afternoon after the lunch, both Brian and myself will be here. We can give more one-on-one demos if you'd like. Also, there's some capability with GIS that has not been demonstrated today for the sake of time. Brian is able to do that. So if you're interested, we can do some more demonstrations after the lunch. Thank you.
Thank you so much, Deb. Thank you, everyone. Now I'll encourage you to put your questions in the Mentimeter. We have one already that was voted up, so I'll start with that one for. Oh, right, I forget. We have a poll question for you. So this is a question for the audience. So please go in Mentimeter and check out our question for you here, which is, how interested are you in these types of information about point source emissions? All right, start. Perfect. One person is voted. Yes, they really want to see this stuff. Excellent. Great, thank you. Thank you. You're really helping us to make some prioritization decisions on what to do next. Okay, so while you fill that out, we will go with the first question. Is our panel ready to take questions? Yep, okay. This use case calls out large emissions, but pivots to focusing on methane emissions. CO2 emissions from cities and power plants are huge. Are there plans to show OCO data that can capture CO2 emissions? And I can also leave that to someone in the audience to address.
I guess I'll start by just clarifying the purpose of the use case for the inventory is to capture emissions that aren't already in there. So yes, cities are large sources of CO2 and power plants as well, but those CO2 emissions are generally captured by the methods that we have for fossil fuel CO2.
And just to follow up on the CO2 thread, so we will be making CO2 available, data available for EMIT. And we look forward to opportunities to intercompare EMIT with OCO 2, 3 CO2 results from power plants as part of our intercomparison. I think we're also open to including OCO 2, 3 data products into future offerings into the data portal. We don't have a methodology that's been ironed out to do that at this point, but over the next year or so, we will, I think, define that.
Andrew, let me just add on to that. So this is Abhishek Chatterjee from NASA JPL. So actually with the OCO3 SAM data, we now have a Jupyter notebook that basically does sort of the same processing and the pipeline that converts the data into this cloud-friendly formats. And we have been talking to Manil, wherever he is, there about that, but we would be certainly happy to accelerate the process. If there is interest within the community, then we can certainly accelerate the process and make sure that the data flows into this use case or some other use case. Yeah.
Okay, thank you. If there are no more questions or no more comments related to that. Okay, another question. How can we ensure equitable monitoring of point source methane emissions from oil, gas, ag, given that space-based detections work best for countries with low cloud cover and high sunlight year-round?
Yeah, that's a tough one. With our current offerings with EMIT and AVRIS 3, obviously we are, like any satellite instrument, we will struggle in the same way with low data densities in the tropics and, coverage that is limited to certain regions historically because of our target mask, which was, primarily focused on the arid regions of the world. We're going to really try to open that up. This is a work in progress. We're going to be trying to look at, there will be a US focus given we are funded through the US Greenhouse Gas Center. So there'll be CONUS prioritization for mapping, but we'll also be looking for opportunities to get coverage of areas that we haven't been able to focus on in the past. And that could include areas where cloud coverage is a problem. I think one of the benefits of instruments like EMIT and other fine spatial resolution instruments is that indeed we can look between the clouds. There are some, it's a bit challenging, cloud shadows. Clouds are a little challenging, but we have seen nice examples of plumes between clouds in the Permian as an example. So there'll be opportunities for us to do more looking at some of these other parts of the world.
Andrew, just to throw another comment in, I am Anne-Marie Eldring from NIST in the Greenhouse Gas Measurement Group, but I think one of the slides we included here is important because it's pointing to where we're heading in the future, that this is a template in these great first examples, but we have missions that have wider swaths, so they might give us opportunities to more observations. We have activities like Carbon Mapper that are smaller satellites, but many of them. And so the technologies that are coming down the road, but maybe not focused on that notion of equitable, they are focused on that notion of high frequency revisit as much of the world as possible. So I think we're heading in that direction. Take some time to get there, but definitely moving in that way.
Okay, thank you for those comments. Have you considered using university and research organizations to obtain monitoring data generated by other parties where the data won't be otherwise provided due to privacy concerns? Maybe I'll invite my colleague to respond to that one related to open data.
Yeah, so I do think that, privacy concerns is really something very important for us. And as I mentioned at the overview introductory presentation, we are thinking of developing a set of methods and approaches for integrating additional data from outside the federal government. For the time being, we have been focusing on really fleshing out these initial focus areas, working across these 4 initial implementing partners. And so within the next year, we will be both enhancing our engagement and then developing the right level of processes and criteria for integrating information from other entities, including universities, including private sector. So not at, we can't give you an answer today, but that's definitely something within the scope of what we're thinking. Thank you.
Okay, and we have a couple of more technical questions. So I guess I'll go into, will the information be presented in spatial entities other than regularized grid? Polygons, cities, counties, etc.
I think when we're talking about the EMIT results in the short term, they're gonna stay in their current format. So that's going to be sort of rasterized concentrations on a per pixel basis. That are limited to snapshots in time, right? We'll be transparent about that. It's a single observation of a methane or CO2 plume at a specific time. Going forward, I think we'll be looking for opportunities to look at repeat mapping of areas, and there's an opportunity to, calculate, how many observations the plume has been seen relative to total observations. There's opportunities to look at expanded data products and offerings that might not be quite as point sourcey in origin. But I think that's something that needs to be worked on in the coming months.
We had a similar question related to the point source event data are very interesting, but can we assume fluxes are 0 elsewhere?
So that's a great question. And I think one of the challenges that we've had, particularly with the EMIT mission, is communicating effectively that we're not getting global coverage plus and minus 56 degrees, right? And we've been focusing in the first year of the prime mission on arid regions. So I think that that's a good opportunity, and I've heard this before, it's an opportunity for us to do a little bit better in communicating that going forward, right? To emphasize that if you don't see a plume somewhere, It doesn't necessarily mean that we've imaged it right, and we need to make that clear. I think going forward, when we do a more concerted effort to do mapping in a more systematic way, focusing on greenhouse gases, I think we can do a better job at communicating that.
Okay, can we take some questions from the floor here? Can I invite you to come to the mic? Line up if you have.
Is this thing on? Yeah. Hi, everybody. Riley Duran from Carbon Mapper, and also a veteran of over 10 years of the NASA Carbon Monitoring System program. So I'm super excited to see all this come together, including some products that have been in development for over a decade. I have a couple of recommendations and then a question. Recommendation one, building on what Andrew was just saying, is that one of the challenges of pulling together a very diverse set of data sets like this at different spatial scales and sensitivities is a lack of clarity on what they're really telling you. And so one recommendation is to generate some sort of completeness metric that tells you what the real information content is. Because for most of the applications we've talked about today, completeness is a function of sensitivity or detection limit, spatial coverage, sample frequency, and the distribution of emissions you're trying to see. So for Melissa's example of trying to quantify blowouts, unplanned fugitives, or maybe inefficient process venting, that's one distribution, and you optimize data sets to answer that question as opposed to finding lower emitting sources for leak detection. So that's one thing, is try to generate heat maps and completeness maps so we understand where we have understanding, where we don't. Second recommendation is around standards. I think one of the biggest roles the federal agencies can play is establishing common standards and definitions for things like what constitutes a 90% detection limit. What are reasonable standards for uncertainty quantification? Importantly, validation and calibration of these data sets. If you really want to play a role in lifting the rest of the ecosystem, establish those standards and frameworks and federally funded testing programs so that everybody can bring in all these other data sets. Because a vast majority of the data out there is non-government, and I think you can help lift a lot of ships doing that. And the third thing is a question, and that is, data is great, but our experience is it only gets you about halfway there, and I'm talking about the handoff challenge, and that is interpreting the data, answering questions of users, ingesting their needs, and making sure that data is responsive to it. That is a huge part of the job that traditionally we do not address with data centers alone. So my question is, on the federal program, what are their plans for providing a service aspect of this, including people, humans, not ChatGPT, that can translate and persistently help people understand and use this data, not just put it into a data commons? Because that's a straight up question. End of comment.
I can take a stab, and then, we do have a lot of our colleagues from our interagency team. So what I may do is invite others in the audience to offer, their thoughts as well. I realize I should have probably done that with some of the other questions, but some of you could have jumped in anyway. So please do now. So yes, so we do, we have discussed the possibility of having some sort of help desk. We're not there today, but we have been thinking about opportunities to providing, and so we will be using actually our stakeholder engagement and efforts to define maybe some of the requirements for something like that. So what would that look like in terms of providing support, both in terms of using some of the capabilities and products from the center, but then also helping with the interpretation part that you mentioned, Riley. And so that's just one aspect that we have been considering, and we're not there today, but it is part of, what we would like to do as part of an offering of the Greenhouse Gas Center. In the Focus Area 2 presentation, you saw some of the things around developing the workforce through summer schools or potentially trainings that are really bi-directional, maybe involve some of the users actually being part of the trainings as trainees, trainers themselves training others. And so we have been thinking about ways to do that and to really help both develop the workforce and also engage different types of stakeholders and users in knowledge transfer. There are additional, activities that we have been considering, and so this is definitely, but in terms of the service itself, this is again, we're in the prototype phase. And so we do want to move to a phase where this becomes a sustained use system. And as part of that, definitely being able to provide a certain level of support that comes along with that is part of our discussions. And so maybe, more to come on this, but I think that's all I will share right now, but I'll turn it over to others from NIST. I know standards were mentioned, so James may have input, Venda, Ariel, other colleagues from EPA, if they want to add, please. And yeah, I see Bill in the audience there.
I think just from a NIST comment, yeah, I think you're right, Riley, that the handoff, right, that's why we're excited to be part of the stakeholder forum. And I think I also look to Shauna to help try to, first of all, get us in better communication with potential end users of this data, understand what they require, and then we try to fill that gap. And as you mentioned, better definitions and more clarity on what the information is that we're preparing is something that's important. So and James had mentioned, I think the NIST model is trying to work with private sector and the government to understand needs, build consensus, and articulate information. It's not quite that handoff I think you're talking about, Riley, but we definitely have awareness that we need to not think we know what everybody requires, but actually talk to those end users and then work as a community to get the information packaged in a way that is useful to them.
Okay, any further comments from the audience? All right, thank you so much for panel 3 and for showcasing the 3 main focus areas for our Greenhouse Gas Center to date. So I wanted to just point your attention to the screen. We do have some QR codes. The first one is for a user focus group, so you can sign up for additional engagements, learn more. We will be having a lot of more discussions, webinars and such related to each of the 3 areas. That's one way we plan to communicate with you and get feedback, portal updates. You heard from Archie's presentation, we plan to do there. And for those online that missed that, this is definitely an opportunity for you to join us in the next year or so and onwards to engage on the focus areas that we have and try to improve them, prioritize, get user feedback and requirements. Okay, so next I would like to bring back one of our opening speakers. I'd like to bring Grace Hugh, Dr. Whetstone and Ariel Stein up to sit and I would like to, yes. And I will turn it over to Grace to give a presentation on the national strategy to advance the integrated U.S. greenhouse gas measurement, monitoring, and information system, which is really a showcase into where the center can go next. Thank you.
Thanks, Shanna. Okay, good afternoon. We're on the last part of the session. So I'm excited to tell you about the strategy that our interagency working group has been working on. And caveat, it hasn't been released yet. It's coming out tomorrow around lunchtime. Office of Management and Budget, Climate Policy Office, and Office of Science and Technology Policy, they'll be releasing the strategy on behalf of the interagency working group, and there'll be a press release out sometime lunch tomorrow with the link. And then I have Ken, are you coming up too for Q&A? Y'all gotta help me answer the hard questions here, right? You're the technical people. Okay, next slide. So some key points. So as you heard today, a lot of the capabilities for greenhouse gas measurement, monitoring information already exist. We're trying to capitalize on an opportunity space to enhance coordination and integration of these capabilities. And so what has happened is we've spent the past year with this interagency working group developing a national strategy to enhance coordination of federal and non-federal efforts to provide trusted, transparent, and accurate data. Some of the questions that the audience has asked today, you've gotten answers from the Greenhouse Gas Center saying, oh, this is not really our purview, or we're not gotten there yet. Some of those topics are intended to be addressed in this broader strategy. And so this Greenhouse Gas Center is a part of the strategy, but the strategy is also broader and includes some longer term efforts to improve our capabilities. Okay, next slide. So what I'm going to do is we have about a 20-minute slot. We're going to do a very quick overview for about 10 minutes and then open it up to Q&A. So the opportunity exists to enhance greenhouse gas information, to take advantage of the areas where scientific and technological advances are moving quickly and leverage current and upcoming observing systems. So, you know, we're OMB, so we're the money people, right? I mean, we've literally invested millions of dollars at the science agencies to come up with some of these capabilities, and we want to make sure we're taking advantage of those capabilities. We also know that there's a rapidly increasing demand from users for trusted information, and what we want to do is really supercharge coordination efforts to accelerate efforts to enhance greenhouse gas information. Next slide. So what is this strategy? It's going to be about a 70-page report that outlines a vision, a concept, and near-term efforts to support a national greenhouse gas measurement, monitoring, and information system. It's going to include cross-cutting objectives and principles that we hope will guide our collective U.S. government, commercial, philanthropic, and science community efforts. We are proposing some demonstration areas and practical actions to improve greenhouse gas information in the near term. And of course, thanks, some of you met today, I know responded to our request for information. Thank you for doing that. It's informed by 2 RFIs and meetings with external stakeholders and experts. Here's what the strategy is not. It's not a detailed implementation plan. I mean, we already got 70 pages. And as you know, on any of these topics, people could have written a whole treatise on any one of these topics. So not a super detailed implementation plan, but a framework to guide our collective efforts together. It's also not a pie in the sky, one day maybe proposal. So there's a practicality inserted into it. So yes, there's a vision, there's objectives, but we are, like the Greenhouse Gas Center, taking a phased, iterative approach. Again, we didn't want to spend 2 years drawing paper plans and then do something. Next slide. So we have a vision. One of the RFI themes was like, what is your vision for this? What are you actually trying to do? Is this a research effort? What is it? So, you know, this greenhouse gas, this GMIS that we're developing will quantify greenhouse gas emissions and removals to support public and private sector climate efforts in the U.S. at local, state, tribal, and national levels. So there's a practical aspect of it. The GMIS will be based on scientifically validated methods with sufficient granularity and space and time, and we'll be working on dissemination of trusted, reliable, transparent, and accurate data. Now you can see the focus is on U.S. climate efforts, but we want to note it is very much extensible to international efforts. And a lot of the agencies in our group and people in our group, they are at the forum, the WMO, Greenhouse Gas Watch, I guess they are involved with those efforts on an international level. So there is a connection, but the initial effort is to support climate efforts in the U.S. Next. So we have some cross-cutting objectives in the strategy, and then we have more detailed sector efforts. And under each of these objectives, you're going to see supporting tasks. So none of these are mind-blowing, but what we want to do is explicitly say, okay, here's what we're going to move towards. Objective 3 is a key theme that you've heard today, which is coordinating, reconciling the use of atmospheric and activity-based approaches, the top-down and the bottom-up, to eventually move toward convergence of estimates and to improve confidence in our estimates. There's also a focus on increasing latency, completeness, interoperability, accessibility of data. There's been a lot of questions today on resolution and frequency of data. I think a lot of those things will be informed by the user groups, because we want to be responsive to user needs. And again, OMB being the money, we want to effectively use our resources. And so we got to focus on areas where we can make the greatest impact. And lastly, another theme from the RFI and that Riley brought up, standards, validation, calibration efforts. And so there's also some content in the strategy on that. Okay, next slide. So in addition to the objectives and principles and the vision that you'll see in the strategy, there's a bulk of the strategies on near-term efforts. So there'll be specific actions to address the objectives that were just mentioned. We also talk about the Greenhouse Gas Center. There's sector-specific efforts on agriculture, energy, and waste. So for ag, we talk about USDA's efforts to set up a soil monitoring network and to better understand and measure emissions from the animal agriculture. For energy, there's a demonstration being led by USGS on coal mines, setting up coal mine measurement test beds and reconciling the top down with bottom up. Peter Warwick from USGS is here today, and he's the lead on that demonstration. There's also a section on oil and gas. Waste is focused on measuring and better understanding emissions from landfills. The next topic has been a topic today and also came up in the RFI feedback, which is ongoing measurement, monitoring, analysis of what's going on in the natural system. And so we talk about in there how, the current way research is done, scientists come up with a short-term research investigation. And so we want to explore the feasibility, like, do we need a more structured interagency research program to support kind of sustained long-term monitoring and analysis? And then last but not least is this urban scale prototype that will implement some of these objectives and themes in a smaller scale, which will inform lessons learned for ramping up. And for that, I'm going to turn it over to Dr. Ariel Stein.
Thank you. So the idea here is to work together with NIST and NOAA, creating this urban scale prototype system. And the key word here is operation. Operation means a consistent way of providing information over time, okay? And that's what we want to perform here. So first of all, we want to demonstrate that we can do this in a sustained way. So basically 30 years from now, I'll be in front of you and we'll be seeing this not prototype, but this operational system providing us with the required information. Also, we want to create this space for sharing experiences and how do we incorporate these new ways of doing science into this operational system. We have to think like this system has a lot of parallels to the weather enterprise, okay? So there are many parallels with that. So we want to combine a top-down and bottom-up systems and design it with enough flexibility and adaptability to incorporate this new science that is coming up, also with the feedback from the receiving end from users. Okay, so next slide, please. And basically, we are starting with the DC Baltimore area. This is an area that has been studied for a very, very long time, and we stand on the shoulders of many people that have been doing this work for the last 15 years. We're going to use the initial data taken from NIST, from the urban GHG measurement testbed. We are going to use some of NOAA's operational models like high split and also carbon tracker Lagrange. And basically what we want to come up is with a cadence of operational information about greenhouse gas emissions in the Washington, Baltimore area, with the potential of using also satellite observational data. Of course, you need to have a first guess, which is the emissions that you use to start with. And an example could be something like what Grapes is using and also what the EPA is providing. So the idea here is that we have already started creating an operational plan, and we are thinking that we can have starting generating this data by FY25. So with that, back to.
Just one more point that we didn't get on the slide, which is that we're also working with Kevin Gurney and Ken Davis, Kevin at Northern Arizona University and Ken at Penn State, in our Indianapolis test bed on a very similar approach. And I think what this will do will allow us to kind of test some of the flexibility that this prototype framework will be developed. And so we'll essentially have two examples that we can try to test the system on. So Grace?
Does this one work? Oh, yes. Okay. All right. Thank you too. And I want to say, I want to thank these three gentlemen to my left here. A a lot of interagency work is kind of thankless work. You do a lot, and on top of your day jobs, and on top of all the, like, Ken is constantly traveling. So really appreciate the expertise, the work, the staff you pulled in to help with this. And last, I just want to say, I know we're short on time. You know, I started off saying where we are today, we're at a starting point, and we want to build this with you and other stakeholders. And this strategy, putting it together, was a forcing function to get our ducks in a row on the federal government side. And so, you know, we look forward to working with you. We definitely want feedback, right? We want to make sure the products and the things that come out of this are useful to people on the ground. And so, you know, whether it's constructive feedback is welcome, and we look forward to continuing to engage with you. And I think we're opening up the Q&A.
Yes, thank you. And again, we will invite you to put your questions in Mentimeter, but I'll also invite folks in the room right now to line up and come to the mic. I'm happy to share this mic with you as well, if you have any questions in the room. The questions we have online are still related to the GHG Center, so I can ask one while you formulate the questions related to the national strategy. So there was one question from DOE, or related to DOE, saying DOE seems to be missing from the planning to date. How can agencies like these get involved?
So we actually had a preliminary discussion with DOE recently on their participation, and RG, we will connect on this, and the natural systems use case, that they have programs like Ameriflux, where they've set standards and data. And so again, this is an iterative approach, right? I mean, just getting 4 agencies to coordinate is kind of a big deal, y'all. So we are exploring opportunities. You know, maybe USGS could be involved with natural systems as well. So we're not excluding anyone. It's just we're building this out, and we are fully intending to talk to those agencies and with the GHG Center team.
I forgot to mention when we were presenting GRAPES, the DOE is a very important part of GRAPES, as well as NASA. Barry Luffer's here. Just a shout out to him. So, and there are other NOAA laboratories that are a part of GRAPES as well. So I just wanted to make sure that they are a very important partner of the GRAPES initiative. So anyways, just.
Thank you. Kevin.
So thanks, Grace, this is really exciting. Looking forward to reading the 70 pages on the flight back, of course. But I was wondering, one of the things I wanted to bring up is, and this was a question as a post earlier. We know in the very beginning of the original draft, it articulated a goal, the administration's goal of, I think, cutting methane emissions by 50% by 2030 and decarbonization by 2050. That's a complete sea change in our entire energy and economy in 25 years. That's pretty ambitious. So one of the goals was, how do we assess that we are on track to meeting those goals, and whether or not, maybe in a projection sense, the arc of where we are versus where we need to be. And so we kind of punted on the question of projections. Do you see, because I didn't see it articulated clearly, directly in the objectives up there, do you see a role for the GHGMMIS to begin to look in that forward posture? Are we in that track to where we headed? Are we looking at scenarios that would better hit that 10-year, 5-year, because 25 years is going to come up pretty fast. How do you see that sort of forward-looking posture relative to building up our capacity to understand what's going on right now?
So the future projection part is not part of the current strategy, but this is not a static document. This is an evolving document, and we want to know what users needs, like through cities and states, how helpful would those projections be? So I think we're open to, in the future, expanding use cases, expanding other things we look at, but for right now, it's not part of it.
I will add, the IPCC has various scenarios out there right now. There is nothing stopping people from taking the data we have on GHG Center going forward for comparing to those various scenarios. That's always a possibility that people can do that. Whether we do that ourselves or not is to be determined.
And then so maybe a feedback from that point would be developing products that would facilitate additional individuals to use things like an integrated assessment model
look how it's going on. A short term, relatively short term, 5, 10, 15 years. That's pretty short.
So you're emphasizing on the verification piece. We are emphasizing on the monitoring piece. So there are different things, and they have political implications that are different. Right now, I think that the emphasis is in detecting those changes and being able to detect them. The path that we take as a society in terms of what are the solutions that we give to this problem, I think that they are in a different realm. But I agree with you that we should provide some kind of path forward in terms of, okay, these are the possible scenarios, but that will require probably the incorporation of, economists and it's a bigger endeavor than just going out there and measuring and monitoring this. Okay.
Absolutely.
Yeah, just to perhaps end it. I think one thing we've heard today that there's a lot of data we don't have. There's a lot of measurements we don't have. I think that, at least Grace may correct me here, but the focus of this activity mostly has been on what can the United States do to get its house in order on this particular topic, and in particular provide, if it were, an exemplar of how to do it and how effective it might be. And so your question about, well, how do we know whether or not we're on track to get to 2030 or 2050 or whatever that target might be, I think is clouded to some degree with what we don't know. So I think we need to improve what we know, and we need to do that with a very clear scientific basis and an emphasis on accuracy.
Okay, we have one question from the virtual space, and then we'll do one more in the room, and then we will close the session. So the federal effort needs to make affirmative steps to include state and local government stakeholders. How do you propose to do this?
So a federal report that comes out, we can only put in stuff that's baked or that we have. So that is an outstanding question that we haven't quite figured out yet. I think there are ideas on mechanisms we could use, and RG has brought up some of them today, but we do realize that states and some cities are really leading in this area, and we need to take advantage of that. So I would say there's the intent to reach out, to partner, to leverage capabilities at the non-federal level, but the mechanics of how to do that and the coordination structures, we are still trying to figure out. And if you have advice on, what those coordination structures or mechanisms should be, because what we also don't want to do is reinvent the wheel and make people attend a bunch of new meetings for a new group. So we could possibly leverage new, existing forums where mayors and city planners are coming together. So we're looking on where can we leverage existing coordination mechanisms, because that will probably be the fastest way to get this input and to accelerate the coordination.
Okay, thank you. And I think we had one more question in the audience.
Thank you very much. George Hurt, University of Maryland, and NASA Carbon Monitoring System. I just have a comment and a follow-on question, I think, to Kevin. I think this effort represents a major step in maturing and operationalizing the greenhouse gas monitoring capabilities that these various agencies have been making huge advances in over the years. So I really welcome this advance. I did want to continue on Kevin's line of questioning. We at NASA Carbon Monitoring System, we work with a range of stakeholders, different cities, states, countries. And when I zoom out to what these stakeholders are really wanting, they need monitoring to know what their carbon fluxes and greenhouse gas fluxes more broadly are over time. But the second big thing they need is a plan for how to reduce them. And so it really is Kevin's question again. It's not verification per se, it's actually planning. Like, how are we going to actually get from what our emissions are right now to net zero by a certain date and actual zero by a different date? What combination strategies are we going to use? And it's not exactly only economists, it is this bigger set of people, because we need to know how our natural sources and sinks might vary under climate change because we can't assume a static climate probably. So it really maybe is a sequel to this activity. It's not a distinct activity. It's not a different group that should be doing it. It should be linked to this effort because that those plans should be consistent with what we know about the current and past.
But George, I'll just add to that a little bit. Much of what you were kind of asking about is really education for the public. So the question will be, how do we develop a good education sets of information for the public to take to actually make those decisions? Right now, we don't have a lot of that. There's a little bit of that in the current website going forward, the GHG Center going forward. But in the long run, we'll probably need to expand that if that is our goal.
That was really a great point. I'm not sure that we have all the expertise here to create those kind of plans. Those will be plans to bring you from what the emissions that are today to the emissions that you will have 20 years from now. I think it's probably a great follow-up from as a feedback from the stakeholders in terms of what the real needs are. One thing is to know where you are in that line, in that map, in all these maps, where are we going? But then, how can we land this? And they're different. I think it's a great point.
And George, as well as I do, being involved in CMS over the years and interacting with stakeholders, is they come up with a lot of ideas and a lot of them we can't do. But hearing the stakeholder needs is the first place to start. It always is the first place to start.
Okay, thank you, everyone. Thank you to all of our presenters, our panelists, and attendees, both in person and online. Today was a fantastic first conversation with engaging with the U.S. Greenhouse Gas Center, and we look forward to engaging with all of you in the months ahead. Now, I just wanted to remind you that this was our initial early feedback with you, our first engagement. This was invitation only, and it's a quick reminder to refrain from publicizing our portal until our official announcement, which releases during COP December 4th. We have a poll on Mentimeter as well that we will like for you to continue to provide us feedback with. But before we do that, I wanted to show one slide that came from RG's presentation about what happens next. So we do have more public engagements that we do plan to have. Some of them in the more technical conferences going forward. We have COP. There'll be a presentation during the COP, the side event for the US Center. The strategy will be released very soon, as you heard. AGU is coming up, and we'll have some presence there with presentations and so forth. Same thing for AMS, more presentations and potentially a training. We do plan to engage. Someone asked about the states. We do plan to have some more focused engagement with the US states, and we've started that discussion. I deliberately invited our colleagues from the US Climate Alliance here so that we can start those conversations. And we have additional meetings going forward. There should be another release of our portal in April, if you missed that, what RG mentioned. So we will be doing another initial release, and we'll need your feedback on that to get us there and also how we did. So please remember to sign up for these user focus groups that we have. And then we'll do a full release by the end of next fiscal year, by about September of 2024. And another one of these workshops, but bigger, longer, more people talking other than us, that we plan to have next year as well. So I know some folks couldn't come because of their planning budgets and travel budgets, do put it in a placeholder for a meeting next year, possibly around the same timing as now. So yeah, thank you again for doing that. So can we bring up the Mentimeter? Okay, so from the folks in the room, which one of these focus areas interested you? Oh, interesting. More on the natural sources and sinks. Okay. Okay, so it looks like we did a pretty good job in getting some interest, or the needs met at least, or interest being met by the portal. Excellent, thank you. I guess we can scroll to the next question. Those who haven't answered, yes, please continue to put it in. So based on what you've seen today, do you anticipate using the center portal in your work? And yeah, it'd be nice to see, yeah. And the good thing, the reason we wanted to know this is we want to know how can we make this portal better. So there's a comment section in the Q&A, and we also have the website. There's the contact us, and there's forums, and then there's these focus groups. We want to know how can we do better. If we can't help you in your work right now, what can we do to help you in your work? So please do provide us with that feedback. Okay, and for the final one, so how interested are you in the following potential capabilities for the U.S. Greenhouse Gas Center portal? Again, we're looking into new enhancements coming up for the next beta release in the spring and again in the fall. So we need to make some prioritization decisions and some discussion with you about what kind of things you want to see there. And again, we'll have more detailed discussion about these topics in our user focus groups for those that signed up. So, and for those who want to give us more feedback at the various conferences that we'll be attending over the next year or so. And finally, how interested are you in in-depth training in the data sets for the following, the three focus areas that you learned about today? I know we had some interest from our training teams, at least at NASA, and there are others in the other agencies that were just looking to see what do people want to hear about? What should we provide via the services that we currently have? How can we leverage the existing trainings that are there? Okay, so focus area 2 looks like there are more training needs necessary. Great, thank you. And now this one will be, I think this is the final question. Yeah, so this one's open for you to write comments. You'll probably have to write comments in the